Uh, इतना क्यों नाज है इसमें क्यों क्या करूं ओ बहुत पल में खुश है पल में खफा बदल रंग हर घड़ी और जो भी दे तू उसका लगती है तेरी बड़ी
Sean, are you there?
Yes, sir, I'm here.
Okay. We'll start sharp at 5, okay? Good evening, Pare sir. Please turn off your videos. Good evening. Good evening, sir.
Good evening.
Yeah, good evening. Can you hear me now?
Yes, yes.
Yeah.
Everything is fine. Okay.
Can we test the sharing of the screen?
Sure, sir. Sure, sir.
How do I do that?
Sir, you will see that share screen option is there. Sean, please help, sir. Sean, are you there?
So active.
Yes, sir. But can you tell me the name who needs to share the screen?
Professor N. Shottamurthy, sir, is there.
Yeah, Narayanasamy Satyamurthy. Yeah.
Okay, sir. So you would have an option right below at the bottom to share. I'll give you the rights. Please try sharing it.
Okay. It says host disabled.
Yeah, yeah. Now try it, sir.
Okay. Just one more time. Yeah. So I can say one participant, multiple participants. So I say multiple or I say advanced? Multiple? No.
Sean, are you there? Sean,
Yes, sir.
please help, sir.
I have to let me open my file.
Sure,
Yeah,
sir.
sir. So
Definitely.
open your file first and then click on share. You will a pop-up will open where you can see your file. Just select that specific file and click on share.
Okay. Just give me a minute.
I request all other participants to keep their mics muted throughout the course of our webinar.
Thank you, sir.
Yeah, you got it now?
It's coming, sir. Yes, sir. Yes, sir. The chemical bond.
But so I will mute until you give me a cue. Yeah.
Yes, sir. Yes, sir. Yes.
Sir, I'm stopping the presentation. Once Dr. Mitra hands it over to you, you can present the thing again and start yours. Thank you, sir.
Sean, can you hear me?
Yes, sir. Loud and clear.
Okay. Let us start. Okay.
Let's wait for 2-3 minutes more. We have got 434 participants with us. Let's
Okay.
start
Okay.
full house.
Okay. 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 Thank you. Okay.
Hello, sir. What is the timing of the webinar?
Good evening, Sean.
I request all the participants to keep their mics muted. Do not turn it on throughout the course of our webinar. I guess we have got all the speakers with me, Mitra sir, so it's good to go. We can start. We even have got 480 plus participants.
Okay,
So it
thank you,
seems a good
Sean.
platform and we are good to go.
Okay,
Just make sure we
Thank
have got all the speakers with us.
Professor Brajesh Pare.
yes. Pare sir is there.
Pare sir is there. Everybody
Yes,
is there,
yes.
Amrit?
Yes, sir. Yes, sir.
DV Prabhu.
Okay, okay. Prabhu sir is there.
Yes.
Yeah.
Aninda Datta sir
Ravi
is there. Just
Ravi sir has also,
okay.
also joined.
Uday, yes, yes, yes. Uday sir is there.
Yeah.
Okay.
Yeah, everybody is there. So better to start,
Yes.
Amrit.
Okay. Thank you, sir. Good morning, good afternoon, and good evening to all of you wherever you are. A warm welcome to all of you to our national webinar, Scintillating Chemistry, an initiative of ACT East Zone. It is a great privilege for all of us to have all of you amongst us on this particular platform. What a unique assembly today. All of us from various parts of the globe are united digitally. May I now invite Professor S.P. Singh, the Zonal Secretary of ACT East Zone, and the Chief Coordinator and the mastermind of this particular webinar to deliver the welcome address. Over to you, sir.
Singh sir, can you please unmute yourself and put on your video?
Vidvatam cha nirpatvam cha naev kadachanam swadesi pujyate raja vidwan sarvatra pujyet.
So your video
Honorable
is off.
dignitaries.
So your video is not visible.
Yeah, I think it's clear.
Yeah, perfect, sir. Perfect.
Honorable dignitaries, organizing team officials and participants. I feel honored and grateful indeed to see you all in the ACT National Webinar, which is an initiative of ACT East Zone. It's pleasing to share with the participants that all the resource personnel today are exceptionally motivating speakers and inspiring leaders. Their presence at the webinar will prove to be highly beneficial to the chemistry fraternity who will witness this event. The team ACT extends its heartiest welcome to the dignitaries present today in the National Scintillating Chemistry. We salute you, sir. A diamond has extensive covalent bond with carbon taking the lattice point in sp3 hybridized state sharing all its 4 valence electrons in bonding. This metastable giant allotrope of carbon can be quoted as the message of this national webinar. Its luster is exhibited a multi-step process called cutting. If we need to make the chemistry glow as a central science, let us all put our contributions together, bind ourselves, and make a mass unit, ready to be refined whenever needed. In view of the same, let me have the opportunity to welcome Professor N. Satyamurthy sir, founder and former director of ISR Mohali. Professor Satyamurthy is a recipient of prestigious Shanti Swarup Bhatnagar Award. Welcome you, sir. Diamonds are extremely hard, but also brittle and can be split up by a single blow. Therefore, diamond cutting requires skill, scientific knowledge, tools, and experience. In the same tune, I would like to welcome Professor V. Mitra sir, professor from Indian Institute of Science, Bangalore, and recipient of prestigious Shanti Award. In kinetic theory, they say the total kinetic energy of a system is conserved, and constantly fraction of molecules colliding and bombarding with one another tends to lose energy or gain energy. Maybe, I think, fortunately, the organizing team is on the gaining side in this webinar. I cordially, respectfully welcome Professor Anand Datta, a well-known professor from IIT Bombay. In kinetic theory, Lowell, as he said, that we will be energized today. Exactly like a Maxwell-Boltzmann plot, more and more information will be passed on by our research. I feel some of us will be energized. Here is not exceptional, but ever. It's a great pleasure to welcome Dr. Prabodh Chaube sir, former Senior General Manager, Head R&D Center, BASF India. BASF is an acronym for Badis, Aniline, and Soda Fabric. A German chemical company and the largest chemical producer in the world, sir. I welcome the organizing team members. First of all, Professor Grace Pare, ACT President, one who is chairing the session. And the strongest pillar of ACT, Professor Damodar Prabhu sir. ACT East Zone Vice President, Professor P.M. Misra sir. Coordinator of this webinar, Dr. Executive Council, Dr. Nayan Kamal Bhattacharya ji, Dr. Suresh Arya ji, for your valuable contribution in organizing this webinar. I am sure that a long-range orderliness will prevail from the beginning till the end of the webinar. I welcome all the participants. Thank you very much.
Thank you, Professor Singh. Thank you, Professor Singh. Now I would like to request our very respected Professor D.V. Prabhu sir for his introductory addresses. Over to you, Prabhu sir.
Hello, good evening. Am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Good evening, dear friends. A very warm welcome to Professor Satyamurthy, the founder president of Association of Chemistry Teachers, at whose feet I learned the basic principles of managing this association. Warm welcome, Professor Satyamurthy. Let me first congratulate our very dynamic Professor Subhash Prasad Singh, Secretary of the ACT East Zone, and the young dynamic Dr. Amrit Krishna Mitra, our AC member, for planning and organizing this national webinar on scintillating chemistry. You have chosen a very attractive title, Scintillating Chemistry. Yes, chemistry is scintillating for several reasons. It is a continuously evolving subject which gives us all the basic requirements and also some new materials with fascinating properties like the superconductors, nanomaterials, nanomedicines, then fullerenes, etc. Chemistry is a central subject with linkages with all other sciences, resulting in several interdisciplinary subjects. Just to name a few: chemical biology, geochemistry, chemical oceanography, biophysics, so on and so forth. Environment science and green chemistry, along with materials chemistry, are the new areas of chemistry in which a lot of research is going on all over the world. Environmentally friendly processes are being developed using green reagents. Indeed, go green is the new buzzword in industry. Chemistry has several challenges ahead. Development of non-renewable sources of energy, like the nuclear fusion, in addition to what is happening today, solar energy, wind energy, biodiesel, which is coming up. Then synthesis of biodegradable plastics and plasticizers. Development of new catalysts like heterogeneous catalysis. And very importantly, conversion of waste into energy and biogas, in which our central laboratory, NERI, is actively involved. Science education, as we all know, is undergoing rapid changes, and we have to be prepared for that. Education 4.0 means technology mediated education, in which ICT will play a very dominant role. And the recent COVID crisis has made us aware how technology will play an important role in teaching and instructions. Fortunately, chemistry is a very popular subject in India, and we have a large enrollment for this subject. We have in our country world-class research labs where frontline work is going on in several areas. And in today's webinar, we have four very distinguished scientists who will deliberate on their fields of expertise. Professor N. Satyamurthy, Honorable Professor at the Jawaharlal Nehru Center at Bangalore, former Director ISER Mohali, and as I already said, Founder President of Association of Chemistry Teachers. Then Professor Uday Mehta, IISc Bangalore, Professor Anindya Datta, IIT Mumbai, and of course, Dr. Prabodh Chobe, former General Manager, BASF India, and a well-known educational consultant. I think we have got a galaxy of experts who will talk to you on different aspects of chemical sciences. Association of Chemistry Teachers is a national registered association of chemistry teachers in India and is proud to be associated with this national seminar. Since its founding in 2000, the association has been promoting excellence in chemistry education by organizing national and international conferences and very active participation in the Indian national and international chemistry Olympiad programs. And many of the top chemists, top chemical scientists are involved actively in the chemistry Olympiad program. I have had a good opportunity to be associated since 1999 when it started, and I have seen its growth to one of the topmost competitions in the world. The Association of Chemistry Teachers gives academic support to a peer-reviewed chemistry journal, GP Globalized Journal of Chemistry, which is abstracted and indexed in Chemical Abstracts USA. Its ISI impact factor is 1.022, and it welcomes papers on all areas of chemistry. I am very glad that a large number of participants, more than 2,000, have registered for this webinar. And I would like to once again congratulate Professor Subhash Prasad Singh, Professor Amrit Mitra, and all their colleagues for the successful organization of this webinar. And I'm sure participants will take with them something very, very valuable from the 4 distinguished experts. I wish the webinar grand success. Thank you very much.
Thank you, Professor Prabhu sir. The speakers of today's webinar have such.
Mitra sir, your mic has been muted. Please unmute it.
Am I audible?
Yeah,
Sean,
loud
am
and
I-
clear.
oh,
Yeah, loud and
oh,
clear. Please
oh.
proceed.
Thank you, Professor Prabhu sir. The speaker of today's webinar have such an illustrious list of achievements that if we talk about their achievements alone, the entire duration of the webinar will be exhausted, but the list may not end. We have always known them to be extremely helpful to our students and extremely dedicated to the service of education. They have always supported chemistry community with their unquestionable sincerity and commitment. We welcome you, our honorable speakers. The first speaker of today's program is Professor N. Sattamurthy sir. Words fall short to describe his brilliance. Professor N. Sattamurthy sir was the founder director of Aizar Mohali. Sir was honored with the prestigious Shanti Sharup Bhatnagar Award in the year 1990. May I now request sir to take over, please. Thank you.
Thank you, Dr. Mitra. Can you hear me?
Yes, sir. Yes, sir. You are audible.
Yeah. So I want to thank every one of you, Dr. Singh, Dr. Mitra, Dr. Prabhu, Dr. Pare, and all other colleagues of ACT and other participants for giving me this opportunity to share with you some of the thoughts on chemical bond. Those of you who attended the annual meeting in Chennai a year and a half ago have heard me speak on this subject. Still, I thought I would speak on this subject because now we have a larger audience, and chemical bond ultimately is central to chemistry. Now I would like to share my screen, hopefully. Can you see the screen now?
Yes,
Yeah?
sir. Yes, sir.
Yeah.
Yes, sir. Everything is fine.
Okay. So what is a chemical bond? Of course, how do I go to oh, now I got it, yeah. The famous hero of the movie James Bond would introduce himself. My name is Bond, chemical bond. Sorry, he would say James Bond. But here I would like to talk about chemical bond. The simplest way a chemical bond was defined was by G.N. Lewis, who simply said a pair of electrons held jointly by 2 atoms would constitute a chemical bond. Notice that he did not say it is a covalent bond. He simply called it a chemical bond. Linus Pauling, in his book, gives a little longer definition. There is a chemical bond between 2 atoms or groups of atoms, and the forces acting on them are such that they lead to the formation of an aggregate. The current definition given by IUPAC, International Union of Pure and Applied Chemistry, more or less says that. So what is important for us for the rest of the discussion is that A set of electrons are shared by two or more atoms in a molecule, or sometimes even between molecules. The classic book on the subject is The Nature of Chemical Bond. This is not the original edition. This is a copy that I got when I was a student. It was available for a small amount, 50 rupees or something at that time. But that was my first introduction to the subject. Now, since we have an audience which consists also a large number of students, the discussion will be pedagogical in nature. So I request some of my colleagues, teachers, to bear with me in some places if I am oversimplifying things. So for the students, I would like to emphasize that you can define various bonds: covalent bond, an electrovalent bond or ionic bond, metallic bond, hydrogen bond, and van der Waals bond. Nobody calls it a van der Waals bond. There is a reason for it. If we get time, we will go to that. But if you notice, I have used the word directional for a covalent bond and also for hydrogen bond. In the case of ionic bond, the whole crystal has the ionic interaction going between the ions. In a metallic bond, the bonding is there in the entire piece of metallic crystal. So the covalent bond is directional most of the time, but there are some situations. The simplest species is H3+, where you have a pair of electrons shared by 3 nuclei. There it is difficult to say whether it is directional or not. In the introduction, Dr. Singh mentioned about tetravalent carbon. In methane, definitely it is directional. Similarly, hydrogen bond, when you consider 2 water molecules sharing a hydrogen bond, it is clearly a directional. If you look at the periodic table, this periodic table was produced by a colleague in Delhi University to avoid any infringement on copyright. But it lists all the elements up to 116 or 118. Now, if you look at the bonding, the simplest way, what we learned in high school, is that an ionic bond is formed between atoms on the left side of the periodic table, and an element here, for example, sodium, and element here on this side, a chlorine, forming an ionic bond. And if it is between 2 atoms of same type, like carbon, carbon, the classic one, or nitrogen, nitrogen, then you have a covalent bond. So here I want to emphasize that you can have bonding within a molecule. You can have gases, liquids, solids. Metals are generally solid, but we know that mercury is not solid, it is a liquid. But what we want to talk about in this talk, in this webinar, is the structure of molecules and how the bond plays a very important role in the structure of the molecule. Here I would like to reiterate that when you look at the periodic table, you see a variety of situations. Here are the rare gases. They're all monatomic at room temperature. These are molecules like hydrogen, oxygen. They're all diatomic at room temperature. Ozone exists at room temperature as a triatomic species, but if you go to low enough temperature, it can be tetraatomic. Phosphorus can have 4 atoms in a molecule. Sulfur can have 8. And of course, the example that has come to light in the recent 30-some years is C60. Now we know molecules which are even larger than C60. You can have C80, C120, etc. So you can have a larger clusters where there is bonding between atoms in what one calls a molecule. I'm very fond of telling the students that it is not true that you cannot see a molecule with the naked eye. When you take a piece of metal, you actually see a molecule. when you look at a diamond crystal, you actually see a big molecule. Except that these are special cases. These are giant molecules which you are able to see with your naked eye. If time permits, we will see towards the end some atomic force microscope image of molecules where we are able to see a single molecule and also the bond between atoms in a molecule. In the beginning, Dr. Singh mentioned about diamond, which is very hard. And graphite is soft. Same carbon, one is very hard, the other one is soft, and it is there in your pencil. So when you write, you are removing layers and layers of graphite. Of course, the classic example of C60, you have a molecule that was made in the laboratory. And in the bulk, you can have a C60 crystal. Today, you can order C60 and look at it. I would like to spend some time looking at the history of the development of the concept of a chemical bond. One of the earliest definition was introduced by not this bond by itself, but the stability. Richard Abegg realized that the rare gases have a stable electronic configuration. Therefore, he thought that atoms would try to reach this rare gas configuration. And then in 1904, J.J. Thomson proposed the idea of a shell structure and proposed that in a rare gas, you have a complete shell. In 1916, the same year that G.N. Lewis wrote his paper on chemical bond, Causel talked about electrostatic attraction, but it was special to ionic bond. So this is the classic paper of the atom and the molecule by G.N. Lewis, written in 1916. I do not know how many of you have looked at the journal coming from the Indian Academy of Sciences, Resonance, Journal of Science Education. A few months ago, we celebrated G.N. Lewis, we featured him and reproduced this article. So if you want to read this article, you can go to the Academy website, go to Resonance, and look up the issue focusing on G.N. Lewis. There you will see the reproduction of this article. It's always fun to read the original article and to look at it in a historical perspective. You could see how this giant physical chemist in 1916 was thinking of bond between atoms. His description is captured in a book by Leidler, The History of the World of Physical Chemistry, where he reproduces the structures made by G.N. Lewis, where he introduced the concept of a pair of electrons, where G.N. Lewis looked at each atom having electrons arranged in a cube. Today, of course, we would laugh at it. But remember, this was before quantum mechanics was invented. So he thought of the electrons in an atom arranged in a cube. Of course, it's not true for hydrogen and helium. This is true for other atoms in what you call the first row of the periodic table. So if you have two of them sharing a corner, then you have a sharing of an electron. But when they share an edge here, two electrons are shared, and that constitutes a chemical bond. But if they share a phase, then you will have two pairs of electrons being shared by two atoms, and that would be a double bond. So he was able to use this cubic arrangement to explain a single bond and a double bond. He envisages sharing of three pairs of electrons, but was not able to illustrate with the cubes. Well, there are limitations of this cube model, but the basic idea was there in that paper in 1916, that a pair of electrons constitute a single bond, two pairs constitute a double bond, three pairs constitute a triple bond. Today, we know that there are diatomic species where you can have up to 5 or 6 bond order. That means that many pairs of electrons is shared. I leave it for you to find out what is the nature of bonding between two uranium atoms. The basic idea was actually developed by Lewis even before he moved to Berkeley, when he was still a student at Harvard. But his own supervisor was not ready to appreciate it. So Lewis was very upset about it. Years later, when Harvard offered him honorary doctorate, he refused to accept it. But as they say, rest is all history. But overall, Lewis is a great physical chemist, was a very sad, very unhappy man. His idea was developed by Langmuir. Langmuir acknowledged it, not that Langmuir cheated or any such thing. He acknowledged the origin of the idea from G.N. Lewis, and he got this Nobel Prize for his work on surfaces, not for bonding, but for surfaces. Professor C.N.R. Rao is very fond of saying Lewis should have gotten at least three Nobel Prizes, one for the concept of bonding, one for heavy water or heavy hydrogen, and so on. And G.N. Lewis was found dead in his lab on March 23, 1946. As I said, he was an unhappy man till yet. But whatever he accomplished, all of that was accomplished even before quantum mechanics came in the picture. Now we go to description of a covalent bond using a quantum mechanical description. Classical mechanics talks about Hamiltonian for a system. In quantum mechanics, we have a Hamiltonian operator, you have a kinetic energy operator, you have a potential energy operator. And we learned very early on that you have a time-dependent Schrodinger equation. I'm purposefully introducing the time-dependent Schrodinger equation first, because people normally don't talk about it. But if you really want to talk about chemistry in action, even bonding, you really should talk about the time-dependent Schrodinger equation. But Schrodinger himself used the time-independent Schrodinger equation, Hi equal to E psi, first time in 1926, when he demonstrated the success of his new quantum mechanics or wave mechanics in predicting the spectrum of hydrogen atom. So for an atom or a molecule, you have a kinetic energy operator, which has a nuclear part and electron part. That is the kinetic energy of the electrons and kinetic energy of the nuclei. We all study about the Born-Oppenheimer approximation, where it was pointed out that the nuclei move very slowly when compared to the electrons. Therefore, one can separate the electronic motion and the nuclear motion. And you think of the nuclei being frozen and the electrons going around it. If you look at the special issue of Resonance, I forgot to keep it with me. The cover page shows two flowers coming together and forming a covalent bond. I leave it for you to find it. These are the pictures of Born and Oppenheimer. And this is the Hamiltonian. Those of you who are allergic to seeing equations and operators and so on, I would say don't get scared. Here is a description for completeness. To emphasize, you have to talk about the kinetic energy of the nuclei, kinetic energy of the electron, electron-nuclear attraction, electron-electron repulsion, and nuclear-nuclear repulsion. You may do an approximation where you don't consider the kinetic energy of the nuclei. Then in that Born-Oppenheimer approximation, what is called a frozen core approximation, or frozen nuclei, or a clamped nuclei approximation, we focus our attention on the electronic motion. So when you consider the electronic motion, you have the electron's kinetic energy term, you have an electron-nuclear attraction, and electron-electron repulsion. This is what constitutes electronic Hamiltonian. And so when you solve the problem, the Schrodinger equation for the electronic part, you get electronic energy. To this, now you can add the internuclear repulsion, That is what constitutes what is called the potential energy for the nuclear motion. But what is important, if you want one take-home message at the end of today's talk of mine, in addition to knowing what you know already, that a pair of electrons shared by two nuclei is called a covalent bond or a chemical bond. You can have a double bond, triple bond, etc. I want you to remember that the bond is something not static. A chemical bond is something that is dynamic. All the time, the nuclei are moving relative to each other in a diatomic molecule. And if it is a polyatomic molecule, you can have varied motions. So what is important, I would like to emphasize as we go along, is that although we talk about nuclei being frozen and solving the electronic problem, when it comes to the final analysis, we must understand and appreciate that bond is a dynamic entity. Now, here, look at the hydrogen atom. We talk about quantum mechanics, how its success was proven by predicting the spectrum of hydrogen atom. If you look at this, there is a potential energy curve between the electron and the nucleus. You have a Coulombic potential, which goes from 0 when the electron and the nuclei far away, and then going all the way to minus infinity. If it was a classical picture, electron could be anywhere in this potential energy curve. It can go all the way to minus infinity. But in reality, what Bohr pointed out was that there exists a set of stationary states. Bohr didn't know how the stationary states came, but he boldly proposed that there must be stationary states, and the transition between them gives rise to the hydrogen atom spectrum. So it was Schrödinger who pointed out that these are the stationary states, and you get the stationary states by solving the electronic problem for the electron which is attracted by the hydrogen nucleus, and the potential well here supports several bound states. I would like you to remember the concept of bound states, and this is what we call stationary states, because they don't change with time. If an atom is here in this state, in the ground state, it will stay there, but it doesn't mean the electron is frozen. Electron will undergo motion around the nucleus. That doesn't matter, but its energy remains the same. Or it can be one of the excited states, and it emits lights and comes down. Now let us move on. Let us consider hydrogen molecule ion. Although in the beginning of the lecture, I pointed out a pair of electrons shared by two atoms would constitute a covalent bond. You can actually have one electron being shared by two nuclei. So sometimes people would like to call this a half a bond or a bond order half, but it is as good a bond as you can get. It emphasizes the point that an electron is shared by two nuclei. If you try to look at the quantum mechanical picture, you will find the electron density is maximum between the two nuclei. In other words, this one electron can be shared by both nuclei. That minimizes the internuclear repulsion, and therefore this one electron is responsible for the chemical bond or a covalent bond in the case of a hydrogen molecule ion. So if you wish, you can say it is a one-child couple. Now, the more of this method, the operators and so on, I want to point out that H2 plus can be solved exactly in elliptical coordinates. Hydrogen atom is solved in spherical coordinates. Hydrogen molecule ion is solved in elliptical coordinates, as long as you fix the two nuclei at a position. So what is important is that there is a balance of forces. The electron is delocalized between atoms. There is an electron nuclear attraction, and there is nuclear repulsion. So these attractive and repulsive forces must balance each other, and that is when you get hydrogen molecule ion. Now we can add the internuclear repulsion, then as I said, is called the potential energy for the nuclear motion. So here is a graphic illustration of it. If you consider the electronic energy, this is the electronic energy. The two hydrogen atoms, the proton and the hydrogen atom, when they are far away, if you take that to be the zero of energy, and if you bring it together, do a thought experiment, what in German called Gedanken experiment, thought experiment, and you bring the two nuclei together to form the helium plus. That is, when the internuclear distance becomes zero, it has a -2 Hartree. The hydrogen atom has a -1/2 Hartree. In other words, on this picture, you have a fusion of the two nuclei to form a helium nucleus. So we are not talking about nuclear fusion that was mentioned by Dr. Prabhu, but here it's a thought experiment, how the electronic energy changes when the two nuclei come close to each other. But when they come close to each other, there is internuclear repulsion. So you must consider the balance between this attraction and this repulsion, and this is the potential energy curve. So in the Born-Oppenheimer approximation, you have a concept of a potential energy curve, and it is this curve that supports several bound states. So when you have a covalent bond, that means a molecule has a bound state here. As I said, if you want to take one take-home message, that is that a bond is not a static entity, but a dynamic entity where the two nuclei keep moving back and forth and is surrounded by one electron in the case of H2 plus, two electrons in the case of H2 molecule. Now, how to determine the electronic wave function? So what I have told you is a problem where in principle, you could solve it exactly for every internuclear repulsion. But people realized as early as 1926, 27, 28, that is not going to be the global approach. They were looking for ways and means of getting approximate solutions for larger molecules, for larger number of nuclei, and for larger number of electrons. The basic idea is very simple. If you remember, Schrodinger equation is a differential equation. Those of you who are mathematically inclined, you will understand and appreciate. If you can have y1 as a solution and y2 as a solution, the linear combination is also a solution. So the electron, there's only one electron here. It can be associated with the nucleus A, or it can be associated with the nucleus B. And in reality, it is common for both nuclei A and B. Therefore, it is not surprising that the wave function, the molecular wave function, the electronic wave function for the molecule has a component which is for one atom and also a component for the other atom, and that is your hydrogen atom solution. And then one can look at variational theorem, which tells you that this electronic energy has to be optimally varied. It has to be optimal solution with respect to the effective nuclear charge. I told you when the two nuclei are away from each other, each electrons is only one nuclear charge plus one. But if you squeeze the two nuclei together, the electron will see a +2 charge, which means as the two nuclei come together under the presence of one electron, the so-called effective nuclear charge can change. This energy is a function of this effective nuclear charge, and the variational theorem tells you to go for a best solution, which is the first derivative equal to 0. And in this particular case, for H2 plus, effective nuclear charge is 1.24. Now one considers the nuclear motion. As I said, you add the internuclear repulsion to the electronic energy, you get potential energy for the nuclear motion. So that is your potential energy for the nuclear motion. You have a kinetic energy for nuclear motion. That means now you must solve the problem of time-independent Schrodinger equation, not for the electronic problem, but for the nuclear problem, for the nuclear motion. So this is how a potential energy curve looks like. You saw the curve earlier, so I have reproduced it here. This 4 is a mistake. It should be a harmonic oscillator here. This is how a harmonic oscillator potential looks like. At the bottom of the curve here, this can be approximated by a harmonic oscillator, but as you pull the two nuclei apart, the bond is going to break and you have a potential energy of this. So in the harmonic oscillator model, you get a set of bound states. V plus half h nu is the energy. So V equal to 0 is the lowest energy. So these are the stationary states, and these are the bound states for the harmonic oscillator problem. But if you go further, we will not have time to talk about Hellman-Feynman theorem. All it says is that the potential energy, the derivative of potential energy with respect to the nucleus is the force, and it is the force that is acting between the two nuclei that is responsible for the bond formation. It's important to point out some of the undergraduates, if they are listening to this talk, that Feynman wrote this paper when he still was an undergraduate student in MIT. Let us move on to a 2-electron bond or a hydrogen molecule. Can somebody give me some, Dr. Mitra, or somebody give me a signal when we are about 10 minutes or so left? I do not want to overshoot my time because there are other 3 speakers. Okay. So in the case of a hydrogen molecule, again, you go through the same, solve the Schrodinger equation in the Born-Oppenheimer approximation, and you can solve the problem. And now it's important, what I said a little while ago, this was thought of by Hitler and London. What they said was electron 1 could be with the nucleus A, and electron 2 could be with the nucleus B. And they said the product of the two could be the wave function. As the story goes, they were working very hard in the lab, and it was a very stormy night. And then they could not get the solution to the problem. But after they reached their apartment, they realized that if this is a solution where one electron is with A and another electron is with the B, you can have the other combination, electron 2 with the nucleus A and electron 1 with the nucleus B. And if this is a solution, and if this is a solution, and if they both are equally acceptable solutions, then the linear combination also has to be a solution. The moment they realized this, immediately the problem was solved. So they were able to work out the solution to the hydrogen molecule problem in this, what is called the valence bond approach, where you consider electron pair between two nuclei, one electron with A, two electron with B, and vice versa, and the combination of the two. Again, we are going to skip the mathematics, but what is important is the concept. So this concept of Hitler and London was the basis for the valence bond theory. Here is a picture. If you simply consider the exchange between the two electrons between the two nuclei, you get this middle curve here, Hitler-London curve. And this is the valence bond description. This is the true curve, that is experimentally determined potential energy curve for hydrogen molecule. It in kilojoules, it is 458 kilojoules per mole. They got about 2/3 of the energy here. But remember, this was 1927. In 1927, to be able to predict the stability of hydrogen molecule with a 60% accuracy was a fantastic achievement. As I said, this was the Hitler-London, and it is called the valence bond theory. And this was extended by Linus Pauling in a big way, and he got the Nobel Prize in 1954. But much before Pauling, who talked about sp3 hybridization, Dr. Singh talked about it in his introductory remarks. In diamond, you have a sp3 hybridization. The concept of directed valency, which I said is responsible for the covalent bond, was proposed in 1873 when Van 't Hoff was a PhD student. So you can be an undergraduate student like Feynman, you can come up with the Feynman theorem. You can be a PhD student like Van 't Hoff, and you can come up with the concept of directed valency. So you don't have to wait to get gray hair or no hair like me to be able to contribute. When you are young, that is the best time to think of new ideas and make contributions to whatever field that you choose. I want to take a little bit of time and also emphasize that the molecular orbital theory proposed by Mulliken and Hund. Mulliken got Nobel Prize. Hund did not get Nobel Prize. This Hund is the same person who came up with the Hund's rule. He contributed enormously for the development of molecular orbital theory. Here the idea is very simple. Electron 1 can be common between electron nuclei A and B. Electron 2 can be common between the nuclei A and B. If this is one solution, this is another solution, you take a product of the two, and this way you build up the wave function for the molecule. This is a simple case of a diatomic molecule. As you go to larger and larger molecule, the wave function gets more complicated. As early as 1968, 1933, the problem was solved almost exactly. Remember, 1933, there were no computers. And yet, James and Coolidge could get almost the correct energy to the third decimal place in Hartree. In 1968, Kolos and Volniewicz solved the problem to the third decimal place. And what was interesting was they could predict the bond dissociation energy up to here 36,000 wave numbers. 8,000 wave numbers is 1 electron volt. And that's here they said they were so confident. They said, look, experiment has to be redone. So Hertzberg redid the experiment and said, yes, theory was right. And you can see up to the first decimal place, theory and experiment agreed in predicting the bond dissociation energy of hydrogen molecule. Nobel, as I said, Mulliken got the Nobel Prize. Hund did not get the Nobel Prize. And I want to sum it up here. You can have a 1 electron bond, as you see in H2+, or you can have a 2 electron bond, as you have in H2. If H2 has a bond order 1, then H2+ has a bond order half. Then you can build up this story. And as I said, a bond is not a static one, it is a dynamic thing. You look at the internuclear motion in the potential energy curve. Here is the potential energy curve for a hydrogen molecule. And this is the limit where you have 2 hydrogen atoms. And this is the limit where you have a hydrogen molecule. Even in the lowest energy state, H2 is not sitting idle. It is undergoing this motion all the time, like a spring. It can be in any one of the excited states. And here is situation H2 minus. The reason I have shown the potential energy curve for H2 minus is that here this is also a weak bond like H2 plus. It has a bond order half. And it also supports several bound states. But at this energy, there is a crossing between H2 minus curve and H2 curve. Astrophysicists believe that initially it was H2 minus that was formed, which gave rise to H2 molecule. You know, normally in chemistry class, we say 2 hydrogen atoms come together, form a hydrogen molecule. It looks like that is not the truth. It is not the complete truth. What happened in early time of the universe was a hydrogen atom and H minus, they came together, form H2 minus. But H2 minus is not stable in the excited state. It's stable in the ground state here, but not so in the excited state. And very quickly it forms a hydrogen molecule and an electron leaves. But what is still important is that whether you talk about H2 or you talk about H2 minus, the bonding is not a static picture, but a dynamic picture. I want to show this curve here to emphasize there is no difference in bonding nature between H2 plus and H2, but when it comes to H2 minus, the story is slightly different. So one can go on with it. What we need to do is to talk about, so we talked about hydrogen atom, we talked about hydrogen molecule ion, we talked about hydrogen molecule, and we extend the concept to polyatomic molecules. Whether you have 2 atoms or 3 atoms or C60 or even larger number of atoms in a molecule, the basic idea is followed. You solve for a fixed nuclei, you solve the electronic motion problem, add the internuclear repulsion, and then consider the bonding, the potential energy for the nuclear motion, and you get the bound states. And these bound states are what are responsible for all the spectra that you observe, whether it's a hydrogen molecule, or a hydrogen chloride molecule, or a C60 molecule, whatever molecule you consider, it is these bound states which are responsible for various spectroscopy. Here I have the picture of the Kadamba flower, where I illustrate graphically how the two hydrogen atoms can form hydrogen molecule and so on. Now, when you go to polyatomic molecules, I realize nobody is showing me the hand that I have been speaking for about 40 minutes. I probably should stop here. I want to raise this question. In a hydrogen molecule, we know this half is hydrogen, one hydrogen, this half is another hydrogen. But if you don't have a homonuclear molecule, hydrogen chloride, for example, where do you divide between the two atoms? How many electrons belong to hydrogen atom? How many electrons belong to chlorine atom? Or you go to, for example, let me say, water molecule. You see there is a bond between the hydrogen atom and the nucleus, oxygen nucleus here, hydrogen atom and the oxygen here, but there is no bonding between the hydrogen atom. This concept of atoms and molecules helps you understand or visualize how there is bonding between the H and O, but not between H and H. These ideas can be extended to larger molecules. They can be extended to interactions between molecules. We can talk about van der Waals molecules, but we don't have time. So we are going to leave it here. Let me sum it up. What I wanted to convey in this webinar is that electrons are shared by nuclei in forming a bond. A chemist would like to classify them as single bond, double bond, triple bond based on the number of pairs of electrons that are shared between the nuclei. As much as we talk about freezing the nuclei and looking at the electronic motion, actually the molecules are not static, they are dynamic. One is purely for the purpose of visualizing, we think of bond as a static picture, but in reality, we must think of them as a dynamical entity. So I want to thank you all for joining in this webinar and giving me an opportunity to share the ideas. These are not original ideas. These are ideas which have come over a period of more than 100 years by great people in the area of physical chemistry or not. I don't want to say physical chemistry, in the area of chemistry and physics. And today we have this level of understanding. Thank you.
Thank you, sir. Thank you, sir, for enriching us through your wonderful presentation. Our speakers are so eloquent and mesmerizing that we do not want to let them go. We want to continue listening to them and learn more and more things from them. However, unfortunately, since we have a limited time, we may not take too many questions from the participants. We would like the participants to email us all their queries so that we can pass it on to our respective speakers. Thank you, Sathyamurthy sir, for your wonderful lecture. Thank you, sir. I would now like to welcome the charismatic Professor Uday Moitra sir. Professor Uday Moitra sir is a senior professor of Indian Institute of Science, Bangalore. Professor Uday Moitra sir was honored with the prestigious Shanti Sharup Bhatnagar Award in the year 2001. May I now request sir to take over. You are welcome, sir.
Thank you. Can you all hear me?
Yes, sir. Yes, sir. It is audible.
Let me share the screen. Right now, I don't have the permission.
Sean, please check.
Sir, you have it now.
Okay. All right. Can you all see my slide?
Yes, sir. Yes, sir.
And now I'm going full screen. This is a test
Yes,
slide just to make sure that everybody sees everything.
Yes, sir.
All right. Let me also start my timer here. All right. Thank you very much, Dr. Mitra, for the introduction. And I would also like to thank you, Dr. Singh, Professor Brijesh Pare, and Professor D.B. Prabhu for putting together this excellent program that allows many people to come together, which would have been otherwise impossible, especially around the difficulties that we have at the present time. What I would like to do is to talk to you about molecules which break rules. This may sound a little funny, but I will take a cue from what Professor Satyamurthy said. He said towards the end that when we give introductory lessons, we do not always give the complete truth, perhaps, partly because sometimes we do not know what the complete truth is, and perhaps we do not have adequate information about this. So what I would like to do is to highlight a few organic chemistry concepts that we teach right from the high school level to undergraduate and at the master's level. And the students tend to believe that whatever rules or policies that we learn are true. I would like to show you with some examples that that's not the case. There are always molecules which are exceptions. I don't seem to get my screen up. Let me see, share screen. Let me try it again. Share. All right. Okay. You know, in terms of breaking rules, I guess we are very good, especially when we are on the street, right? The latest one, of course, being not wearing masks in public places. But then there are molecules which seem to defy rules, and here I put defy within quotes because they do not quite defy the rules. It's simply that in some cases the rules do not apply to them. So as I said that I will pick up 4 or 5 concepts, would like to show some interesting molecules with interesting structures, and basically to get excited about chemistry. It's primarily because I see a large number of students in the participants, including many undergraduate students. Okay, the first concept is about stereochemistry. When you learn conformation, you learn that in cyclohexane, for example, any substituent in the equatorial geometry is more stable than in its axial orientation. And depending upon the size of the molecule, the extent to which the equatorial form is favored can be small or large. For example, for a methyl group, it is about 1.7 kilocalories per mole, by which the equatorial form is stabilized compared to the axial form. Now, a natural question is, when you have multiple substituents, what happens? And I will like to take the example of an extremely packed cyclohexane derivative, hexaethyl cyclohexane. Each ethyl group is on a separate carbon. Now, as you know that, okay, I think I am clicking on the wrong place.
Perfect, sir.
Okay.
Perfect.
All right. I was going, okay. Is it okay now?
Yes, sir. Okay. Okay.
Okay. All right. So the hexaethyl cyclohexane can have many isomers, of which there is one which can be called an all-trans isomer, which is shown on the right-hand side, which I show with my pointer here. Now, this can have an all-axial conformer or an all-equatorial conformer. And I'm sure that all of you would agree that the all-equatorial conformer must be much more stable, because if one substituent is bad in the axial geometry, having 6 ethyl groups in the axial geometry will be terrible. Sure enough, this compound was made and found to have the hexa-equatorial geometry. So the next question is, suppose you start making this group bigger. For example, go from the all-trans hexaethyl to all-trans hexaisopropyl. which is shown over here in the planar geometry, what would be the conformation? Again, I'm sure that 99.9% of you in the audience would say it should be similar to this. That is, it will be hexa isopropyl in the all equatorial geometry. Just a bit about the synthesis. This is how the molecule was synthesized by coupling this dibromide with nickel, which causes basically a 3 molecules cycloaddition with isomerization of one of these exo substituents. And as you might imagine, that these are all tetra substituted double bonds, very hard to hydrogenate, but they were able to hydrogenate, and they got only one stereoisomer of the product, and it turned out to be all trans derivative. And fortunately, the scientists also had a crystal of this molecule. So they got the crystal structure, and that was a surprise. All the isopropyl groups were in the axial geometry. Okay, so here are examples where hexaethyl seems to follow the rule where all the substituents are in the equatorial geometry, but you make it bigger, and your intuition would be that it should favor the hexa equatorial geometry more strongly, but it's exactly the other way around. So the bottom line here that I would like to emphasize is that what is often not told when you are taught about conformation in cyclohexane is that the rule that equatorial geometry is more stable than axial is true for only monosubstituted cyclohexanes and for multi-substituted cyclohexanes where the substituents do not interact with each other. So I would like the young participants in this webinar series to figure out why the hexa isopropyl, all the groups are in the axial geometry. Another concept that is taught at perhaps in the first year is about the non-existence of a double bond at a bridgehead. This has been variously called Bread's rule and certain other modifications on that. But basically what you learn is that you cannot have a double bond over here. And there are many reactions where you try to form an sp2 center on this carbon, and that seems to be, those reactions seem to be disfavored. So here what you notice is that if you go around the ring in the highlighted bonds, you notice that this double bond in a 6-membered ring is actually a trans double bond, because these bonds are on the opposite sides. So it turns out that 6-membered ring is too small to have a trans double bond. 8-membered ring is the smallest ring that can have a stable trans double bond. So we'll not discuss about that today. But there was a group, again, almost 3 decades ago. What they did is that they said, okay, fine, it may not be a stable molecule, but let's try to find out if this species could be generated under conditions where it can be trapped. So what they did is that they took this iodo-bromo-norbornane derivative and treated it with butyl lithium, which should cause a dehalogenation reaction and produce something like a double bond here. And then the idea of this research group was that if you now have a diene in the reaction, then this double bond being very reactive would undergo a Diels-Alder type reaction and would produce these 2 products. So if you find these 2 products, that will suggest to you that you have something like this even as a highly reactive intermediate. Indeed, when the reaction was carried out in the presence of furan, both these molecules were produced, this being the attack of furan on the top face of the double bond, and this results from the attack of furan from the bottom face of the molecule. And they got the same ratio of the mixtures, regardless of whether they started from the iodo-bromo or a iodo-iodo derivative, suggesting that they're going through a common intermediate, and clearly the common intermediate, which is probably very, has a fleeting existence and very unstable, is one with a double bond-like character here. It is now understood that this is probably a 1,2 singlet diradical. There is hardly any bonding because the 2 p orbitals or here will be nearly orthogonal. Now, having said that, if the ring becomes a little bigger, as I said, 8-membered ring, that can have a stable double bond in it. And here is one example. This was made by Ken Shea, again, 30 years ago, where you have a bicyclo 3-3-1 system with a nitrogen at one bridgehead and a stable double bond at the other bridgehead. Again, this was produced by this synthetic route involving a 4+2 cycloaddition. But what was interesting, if you read the experimental part in this paper, is that the authors say that this molecule was air sensitive. Now, normally, a molecule having an amide or an ester or a double bond should not be air sensitive, right? But it turns out that because the double bond is present at a bridgehead, it is highly strained, perhaps twisted to some extent, and therefore it undergoes spontaneous reaction with air and produces the epoxide. You can compare it with the conditions that we normally use, excuse me, for the epoxidation of molecules such as ethylene. You need air, silver catalyst, 400 or 500 degrees centigrade. So that essentially implies that you can make a double bond at a bridgehead, but it is very, very unstable. Now, let me ask the young participants here to calculate the molecular formula of this molecule that I have shown here. All right. So this, again, kind of gives you an exception to another well-known concept that you have studied. Now, I'm sure that most of you have figured out the molecule has 7 carbons. Don't write anything on the screen or unmute your microphone. This is 7 carbon, 2 nitrogens, and most of you would think that it is C7H14N2. If this is the number that you got, if this is the answer that you got, then you are all wrong, because there are only 1, 2, 3, 4 carbons having hydrogens. This carbon does not have any hydrogen because it's a divalent carbon. It's a carbene. This is the molecular formula. And this is the chemical structure of this carbene. These kind of molecules were made, again, close to about 3 decades ago, and are popularly known as Arduengo carbenes because it was first made by a chemist whose name was Arduengo, last name. And the reason it is highly stable, crystalline, and bottleable, that is, you can put it in a bottle, is because if you look at the carbenic carbon, it's a singlet carbene. So that implies that the carbon is sp2 hybridized, and this lone pair is in the plane of the molecule, or in this case, the plane of the screen in front of you, and there's a vacant p orbital perpendicular to the screen. And therefore, this is a cyclic molecule having a vacant p orbital, 2 + 2 + 2, 6 electrons. So it is aromatic. So this carbene, despite having a 6 electron carbon, is aromatic, and that's what gives it maximum thermodynamic stability. Initially, the concept was that perhaps you need to make it kinetically stable, but so Arduengo initially put large groups such as the adamantyl group to make this carbenic carbon kinetically stable, but eventually he found out that that's not necessary. You can simply have methyl groups, and this molecule owes its existence because it is aromatic. In fact, this is no longer an electrophilic carbene, it's a nucleophilic carbene. And since the discovery of Arduengo almost 30 years ago, more than 30 years ago, this species, this is also called NHC, or N-heterocyclic carbene. There are many examples known, and these are used for transition metal catalyst as a ligand and in organocatalysis. So again, a concept that we have all learned while teaching Reimer-Tiemann reaction, which goes through a dichlorocarbene, is that it's a very reactive carbene. But then there are exceptions to this rule, because when you change chlorine by nitrogen, things change completely. All right, here is, I'm again asking a question to the students to think about, is that can you think of molecules having the general formula CnHn, which do not contain any double bond? So obviously acetylene is ruled out, all right? But there are many examples, and these are actually examples of molecules which have multiple CH groups, and all the carbons are tetrahedrally substituted. That is, they're all sp3 carbons. Here's an example that all of you have read in connection with the structure of benzene. It's probably called Ladenburg benzene or prismane. There's a bigger version of it, which is cubane. It was made by Philip Eaton in Chicago in the early 60s. But these are small, but not the smallest one. So the smallest one is actually C4H4, which is called tetrahedron. Professor Satyamurthy talked about Van 't Hoff. He first gave the idea that a tetravalent carbon has to be tetrahedrally substituted. Here I have a twist on that. I have 4 carbons which are oriented at the 4 corners of a tetrahedron with hydrogens here, 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 and here. Now it turns out that all attempts to make this molecule failed. It is simply because this molecule is way too strange to be made. Let's take a look at a slightly smaller version of this molecule, which is this cyclopropanes fused together with a common bond. Now, this molecule has a heat of formation, which is 60 kilocalories per mole. This gives an idea about its instability. Now, when you try to make one more bond here between this carbon and this carbon to make this elusive tetrahedron, what happens is that the calculated heat of formation is more than double of this. So it packs so much energy that it breaks apart. It breaks apart into 2 acetylene molecules or to a cyclobutadiene that can undergo further reactions and so on. Now, does it mean that it can never be made? So a group of Gunther Meyer from Germany, this was again more than 3 decades ago, they figure out that if they put large substituents, then perhaps this molecule can still be made. So it will still be thermodynamically unstable, but it can be made kinetically stable by putting large substituents at each of the corners. And the idea is the following. If you think about tetrahedron, if you put 4 large objects together, like 4 balloons, okay, I would like the students to try out this experiment, make 4 identical balloons and try to put them together. And you will find that it adopts a tetrahedral geometry. So here the idea is that if you put 4 large substituents, they are as far apart from each other as possible in space. Any other geometry will bring the tertiary butyl groups or the large groups closer to each other. If you imagine breaking a bond here, then these 2 pairs of substituents will necessarily come in close proximity, and that will lead to steric repulsion. So what Gunther Meyer did eventually is to start with this molecule, which was known, and this underwent photolysis, first to form a 2+2 system like this, and then finally decarbonylation to produce this substituted tetrahedron. So this is the first time a tetrahedron molecule was made. And as you can see, perhaps from this space filling representation, that the 12 methyl groups essentially surround the C4 tetrahedron, makes it so much stable that it doesn't decompose even upon melting. This is again a bottleable molecule which has a well-defined melting point. Okay, so we talked about conformation, we talked about bread stool, we talked about tetrahedron, and now another interesting concept that we start teaching right from 12th standard, if not sooner, is about aromaticity. And we always talk about the requirements that the system has to be planar, p orbitals should be in the same plane, and it should be a cyclic system having 4n plus 2 pi electrons. All right. Now, can a pi system or an aromatic system be non-planar? I briefly mentioned that the double bond at the bridgehead is often twisted, which essentially means it's a non-planar. It turns out, again, I'm simplifying it and oversimplifying it because Professor Satyamurthy was the earlier speaker and he's still listening to this, that if you have 2 p orbitals parallel, then overlap between them is the strongest. And this overlap is a function of the cosine of the angle between the 2. So cosine 0 is 1, so you get maximum overlap. But if the 2 p orbitals are perpendicular like this, then cosine 90 is 0, and therefore the system is orthogonal, there is no bonding. But something interesting about the cosine function is that if you start twisting one p orbital with respect to another, even by about 30 degrees, let me show you on the camera, even by 30 degrees, the cosine function does not drop very significantly. Cosine 30 is about 0.87, which means that you have twisted the two p orbitals and yet retain significant overlap. So what do you do then? So you try to make a system which forcibly gets twisted. And this is exactly what Robert Pascal at Princeton did. He created this molecule which has two phenanthrenes here, and in the center you see an anthracene. And this is substituted by two phenyl rings, with the result that in the planar geometry, there will be repulsion between the hydrogen here and here, here and here, and two more here and here. And as a result, the central anthracene ring adopts a twisted geometry, as you can see from the crystal structure. You have the phenanthrene on the left, phenanthrene on the left, but the phenanthrene on the right is almost at an angle with respect to the screen. And you can see that the anthracene A, B, C, A and B seem twisted with respect to each other. B and C seem twisted with respect to each other. So from the crystal structure, the end-to-end twist is about 66 degrees, implying that the average twist between this ring and this ring, this ring and this ring is little more than 30 degrees. And as I said, that cosine 30 is actually a respectable number, not very far from 1, far from 0, but closer to 1. So that's what gives this molecule aromatic character. They of course examined the properties of the anthracene ring and concluded the ring is sufficiently aromatic, in spite of the fact that it is twisted. Now, how much more can you twist? I'll show one or two more examples. And this is a molecule that was also made by the same group. And here, what we will try to do is to view this molecule from this side. And this molecule with 4 benzene rings to form a naphthacene or tetracene has an end-to-end twist of 105 degrees. And for ease of viewing, we will view from this side, and each phenyl ring or the aromatic ring will represent by a single carbon ball. Okay, so this is how it looks like. These two carbons are these two carbons is the ring of the phenyl. 1, 2, 3, 4 phenyls on this side. So you see 1, 2, 3, 4 phenyl rings. These 3 atoms correspond to these 3 atoms on the phenanthrene. And you can see that compared to the first bond, that this bond, which is here, the last bond is at an angle which is 105 degrees. And again, therefore, the average twist between the pairs of benzene rings here is close to 35 degrees. So that's what I meant, that you can twist an aromatic system by 30-35 degrees and yet retain sufficient aromaticity. And in this case, the twisting is made by the imposition of steric strain all around the molecule. Another extreme example was made again by the same group. This is 1997. I will skip this part. In this case, it is basically 2 phenanthrene rings separated by 3 rings in between. So there are 1, 2, 3, 4, 5 rings in between. In this case, the end-to-end twist is about 144 degrees from X-ray. And another interesting property of this molecule is that since this molecule is twisted, the twist can be either right-handed or it can be left-handed. And that will give rise to enantiomers if these 2 twisted forms do not interconvert very rapidly. And indeed, in this case, what Pascal and group found out is that they do not interconvert rapidly, and they could be resolved into enantiomers. All right, this is a slightly different example. This is a much more recent example. When we teach the periodic table, and I think we talked a lot about periodic table during 2019, because it was the International Year of the Periodic Table, we always tell the students right from high school that the molecules, that the atoms which you have on the left-hand side or on the right-hand side, they're all reactive molecules. That is, the alkaline earth metals and the halogens, they're all reactive molecules because they are either one short or one extra electron, and that gives rise to them a high reactivity, and therefore they're unstable in nature. It turns out that there's one element which was discovered to be present in the nature in the free form. This is a paper published in 2012. It received a lot of interest, and this goes back to about 200 years. And this is an ore of fluorite, calcium fluoride, CaF2. The parent ore is called fluorite, and which is more or less colorless and transparent and water insoluble material used in various optical equipment. This is another ore called andesonite, found in Germany, and it was known for more than 200 years. And what they found is that if you break the stone, you get a bad smell. And that's why it was called a stink spar or a stinky rock. As I said, that more than 200 years ago, the smell on crushing was noticed. But during the last almost 200 years, the nature or the molecule which is giving rise to the smell was unclear. People expressed different kinds of suggestions like iodine, ozone, fluorine, hydrocarbons, SO2, F2, and many others, selenium and so on. And a group in Germany finally took up this work. And what they did is that they compared the smell of this with many of these proposed molecules and came to the conclusion. This is just a picture of Mossa, who discovered fluorine in 1886. But as perhaps you have studied in school, that this requires very special arrangements for storage of the fluorine that is generated electrochemically. So what they did is that this group, German group, did is to make these molecules and compare the smell of the broken rock with this. And then they came to the conclusion that the broken rock smells of elemental fluorine. Now, if you try to publish a paper saying that you used your nose to identify a molecule, this will no longer be acceptable in 2020 or in 2012. So what they did is the next best thing, and that is to record fluorine NMR. 19F NMR of the stone was recorded. Of course, it gives a very huge peak for F minus, but there's a very characteristic signal around 425 ppm. We are talking about fluorine NMR, and that matches exactly with what you get from elemental fluorine. So this particular rock, in fact, stores elemental fluorine in small quantities, which is produced in this rock because the rock also contains some uranium, and because of radiolysis, CaF2 goes back to elemental calcium, which gives rise to the color of the rock, and fluorine gas, which is trapped in the rock itself. Now I see I have 11 minutes, so I should speed up a bit. Here's a picture of Donald Cram. You have all heard about Cram's rule. And here's a picture of Cram receiving the Nobel Prize in 1987, I believe. Towards the end of his career, Cram was working on molecules which are cage-type molecules, particularly molecules which have a top hemisphere and a bottom hemisphere which are connected. As a result, when you connect two hemispherical molecules, you create a cage inside. And the work that I'm going to talk to you about essentially makes use of this cage molecule. And the background to that is that he talks about a molecule in this particular paper, and I will give the citation of the paper in the next slide. He talks about a molecule saying that is the Mona Lisa of organic chemistry. And the molecule is nothing but an isomer of tetrahedron. Remember, I talked about tetrahedron earlier? And one of the decomposition products, if you try to make tetrahedron, is cyclobutadiene. Cyclobutadiene, as everybody knows, is anti-aromatic, and therefore it cannot exist in its free form. Many attempts to make cyclobutadiene were unsuccessful because apart from other reactions, cyclobutadiene, when you try to make it, it can undergo some decomposition reaction with oxygen, with light to produce acetylene, and last but not the least, it can dimerize to eventually produce cyclooctatetraene. So you can prevent this by doing the reaction in the absence of oxygen. You can prevent this by controlling the amount of radiation, but how do you prevent a dimerization? So Cramp's cage molecules came to his rescue. So what he did is to put this precursor inside the cage. This is the cage that he made. And the idea here is that once you put the molecule inside the cage, a second molecule cannot go in. So the molecule stays inside, and then you shine light, it produces this. And finally, it loses carbon dioxide to produce cyclobutadiene, which stays happily inside the cage. And I will show you some NMR spectra quickly, which shows that the cage molecule, most of the signals are coming from the cage molecule, but these 4 lines are coming from the starting material, which is inside the cage. For the details, you should read the paper. Upon photolysis, it first forms this. You can see that these 4 signals have disappeared and 4 new signals have come. One is merging here. And upon little more photolysis, it produces this. And finally, when you stop the photolysis at the right time, you get a signal from cyclobutadiene. So this is the first time a cyclobutadiene was observed as a free molecule inside a cage molecule as an independent identity, and it gives rise to a single NMR in the proton NMR, single signal in the proton NMR. And as expected, that if you bubble oxygen through the medium now, it undergoes decomposition. It is sort of like ozonolysis to produce this dialdehyde, which was again characterized by these signals. So therefore, what we learn is that, cyclobutadiene is very unstable, is anti-aromatic. It cannot be isolated, but then there is a special way in which you can kinetically trap it by disallowing it to undergo any further decomposition. So that's the catch. That is, you can stabilize a molecule which is unstable thermodynamically by kinetically stabilizing it. A similar strategy was used more recently by Jonathan Nitschke at Cambridge, where he put a P4, white phosphorus molecule, P4, which is extremely reactive towards oxygen. It has been used in phosphorus bombs in the Afghan war. But what he was able to show that using certain specific ligands and ferrous iron, you can generate a tetrahedral cage and you can trap P4 molecule inside it, and it doesn't undergo oxidation reactions under normal conditions, even in an aqueous system. So you are essentially preventing it from reacting by caging it inside a synthetically created cage, which in fact was spontaneously assembled in this particular case. I will skip the description on the bottom. This essentially tells you how the cage, how it can be uncaged and reacted with oxygen subsequently. I have, I think, another 6 minutes. So I would like to show you another unusual reaction. This is not a molecule, but rather a reaction. Many of you are familiar with multi-component coupling or MCQ reactions, basically where many components are put together for getting a single product. This is not like mixing many reagents and for one reaction. In this case, you are mixing many reagents such as A, B, C, and D, but in a certain way, the reaction is planned so that A and B first react to produce an intermediate. That reacts with C, that reacts with D. A and C do not react with each other. C and D do not react with each other. So to put this thing quickly, is that there are many 3-component reactions, 4-component reactions, even 5-component reactions. And many of these were developed by Eva Yugi in Germany. But the one which really beats the world record, I think it still has the world record, this is a picture of Professor Yugi, who is no more. This example was published again more than 3 decades ago of a 7-component coupling. You see 7 components listed here. They undergo reaction in a programmed way. As I said, that in the first step, only 2 of the components react and eventually produces one molecule in 45% yield, and the byproducts are only sodium bromide and 2 water molecules. I think Professor Prabhu talked about green chemistry in the introductory remarks. And this is an example of a real green chemical reaction where the byproducts are just sodium bromide and water molecule. And most of the atoms listed here have been incorporated in this molecule. The yield is about 43%, 2.5:1 ratio of the two diastereomers, because you see two stereocenters here and here. Professor Satyamurthy introduced you to resonance, and it turns out that quite some time back, I wrote a small article on this a particular species, this particular reaction in February 1996, and you can download it free of cost from the Resonance website. The second slide, the next slide has the mechanism of this reaction, but I would like the younger participants to work it out and find out whether the mechanism is correct, that the mechanism that you have worked out is correct. And I'll quickly skip the next slide. All right, the last example is nucleophilic aromatic substitution. Again, a concept taught in early undergraduate courses. And we all know that aromatic systems undergo typically electrophilic substitutions, but for carrying out nucleophilic substitution, you need an activating group, basically an electron deficient aromatic ring. You need a good leaving group like fluorine, and a electron deficient group like nitro groups. More nitro groups are better. And the mechanism is typically addition, elimination. But Eric Jacobsen, a couple of years ago, published a paper when he talked about a concerted nucleophilic aromatic substitution. There is a very specific example of a pyridine derivative shown here. And this example talks about a fluorine displacing the bromide to produce the fluoro derivative. And they worked out using a very sophisticated kinetic isotope effect analysis at natural abundance to show that this molecule undergoes a concerted nucleophilic aromatic substitution. So whatever we have studied, we have learned in our undergraduate years, again, needs to be taken with a pinch of salt, because there can be exceptional molecules which can promote a concerted nucleophilic aromatic substitution. Okay, I think I'm nearly done with my presentation. I hope that I have been able to show you examples in the 40 minutes or less of certain concepts that we learn at the undergraduate level and beyond. But those concepts need not apply to every single molecule. There are molecules which are exceptional, either because of a kinetic stability. You can make a unstable, otherwise unstable molecule rather stable. Sometimes you can make a molecule thermodynamically unstable, thermodynamically stable by putting in appropriate substituents, and so on and so forth. So while the rules that we learn in our undergraduate years are generally true for most molecules, but there are molecules which seem to defy the rules because simply the rules do not apply to them. So that's the end of my presentation. But since last year was the year of the periodic table, I would like to ask the organizers if I can play the periodic table song, which many of you have read earlier.
Yes, sir. Yes, sir. Obviously.
Okay.
Yes, sir.
Okay. So background. So I will unshare this screen now. Let me stop sharing this screen. Okay. So the background to this song is that this song is called a periodic table song. It was created by Professor Tom Lehrer, who was a mathematics professor at Harvard University. And in 1955-56, he created a song, he said, with a vague tune, which basically listed the elements known as time. So what I would like to do is to play this video, but this video is different from what I have played in other places. This is a song sung by Tom Lehrer himself. And this was recorded in Copenhagen. Let me share this particular screen now and play the music in a moment. Let me see, where is it? Yes, share. Can you see this new screen, which is completely dark?
Yes, sir. Yes, sir.
Okay, so let me play the song. And this is sung by Tom Lehrer in a conference in Copenhagen. I'll take it. This is a 3-minute song. Is that okay?
Yes, sir. Yes, sir. No problem,
okay.
Sir.
So let's finish this talk with a little bit of entertainment on this Sunday evening.
Now, here's a song I always get requests for, but I can't understand for the life of me why. It's simply the names of the chemical elements set to a Gilbert and Sullivan tune. I think the only reason I do it is to see if I still can. We'll try. There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and doped actinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. Yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. I left out one, actually. A new one was discovered since the song was written. It's called Lawrencium. So those of you who are taking notes can write it down in your programs. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium, manganese and mercury and lindon, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium, tantalum, magnesium, titanium, tellurium, and cadmium and calcium and chromium and curium. There's gold and californium and fermium.
Sir, the video has stopped. Can you please share it again?
And argon, plutonium, rhodium, and rhodium, and chloride, copper, copper, tungsten, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Hello, so your screen sharing has stopped. Can you please reshare it?
Thank you. You may be interested to know that there is an older, much earlier version of that song, which is due to Aristotle.
I'm not quite sure what happened because I seem to have.
Can you just reshare your screen, sir?
Yes. Did it stop in between?
Yeah, that stopped in between. Just reshare it and we'd be able to begin it again.
Okay, just a second. Give me a minute.
Yeah.
I will play it from. I'll play it from the middle. Sorry about the technical glitches, which are always. Is it okay now?
Yes, sir. Yes, sir.
Yes,
okay.
perfect.
Okay, so let me bring it towards the end.
Has come to Harvard. And there may be many others, but they haven't been discovered.
Let me stop sharing the screen. I hope that despite the technical issue, you have enjoyed the music. And perhaps when you go back and look at some molecules that seem to not follow the rules, you will remember this talk that not all molecules are required, in fact, to follow rules. I would like to thank the organizers again for giving me an opportunity to share with you some thoughts this evening. And thank you very much.
Thank you, sir, for your enthralling presentation. Sir, you reminded us of famous scientist, Professor Robert Barnes Woodward, whose lectures at the University of Harvard would carry on into night, and students would sit transfixed listening to him speak. Thank you, sir, for inspiring our generation. Before we move to our next speaker, I have one important announcement for all of you. Dear participants, please keep checking the chat box from time to time. Filling in the feedback form is mandatory for receiving the certificate. I would now like to welcome our very own Professor Anindya Datta sir from IIT Mumbai. Sir was honored with the bronze medal from Chemical Research Society of India in the year 2018. Sir is extremely popular among students for making spectroscopy easily comprehensible. May I now request sir to take over, please. You are welcome, sir.
Thank you, Amrit. Thanks for the introduction. Thanks for having thought of me as a part of this program. It's a pleasure and honor to be here. And it is humbling to be sharing the podium with urban legends from what now seems to be our childhood, Professor Satyamurthy and Professor Maitra. They have been seniors and mentors for me in many different ways. So thank you very much for having me here. I'll share the screen and we'll begin right away. Here we go.
Yes, sir. It is perfect.
Okay. So today I'm going to talk about our interest that has developed over the last 6-7 years in developing solid-state organic photoemitters. Now that might seem to be an unusual thing for somebody whose primary occupation is to do fluorescence spectroscopy, but I'll try to explain how we come into the picture in a field like this. Now, see, solid-state organic photoemitters have become very, very important over the last decade or a decade and a half, because as we know, organic electronics has arrived. It is no longer a part of some distant dream. It doesn't seem like science fiction anymore. We actually have around us this kind of screens that you can fold and put in a bag, or this kind of an IC, a chip, which you can fold or wear on your shirt or carry with you, or a keyboard that you can fold like this. So one important component of organic electronics is substances, organic substances that would emit light in their solid state. Because naturally, you cannot have a screen that is liquid, right? You want it to be solid. And the main problem with that is that, right, fluorophores are there a dime a dozen. A lot of us would be able to name a lot of conventionally good fluorophores. The good thing about those fluorophores is that they are typically very strongly fluorescent in solution. Whoever is marking the screen, could you please stop? Thank you. It's distracting. So I'll end up telling a different story than what I intend to tell today. All right. So conventional fluorophores, the good thing about them is that they're strongly fluorescent, of course, otherwise they wouldn't be called fluorophores, but usually they're fluorescent in solution. The moment you try to make aggregate out of it, or the moment you try to make a crystal or put them in solid matrix, the phenomenon that is conventionally known to take over is now called aggregation causing and abbreviated ACQ. And this is a very major phenomenon that kills fluorescence in solid states. As we go ahead, I'll try to show you how this ACQ has a role to play in messing up things that we want to do. So the way out, as has been realized over the last decade and a half, is in fluorogenic molecules. Now, the term fluorogenic molecules have had a particular connotation for a long time. What we mean by fluorogenic molecules is molecules that are not fluorescent as such, but would become fluorescent upon some physical or chemical input, complexation with a metal ion, or a reaction with an organic molecule, or solidification, or something else, or temperature for that matter. So these fluorogenic molecules typically would have flexible structures. And that flexible structure would usually render it not all that fluorescent in solution, because flexibility invariably opens up a lot of non-radiative relaxation pathways. So when you take a molecule like that, which is not so fluorescent in solution because of its flexible structure, and you make a solid out of it, or you make an aggregate out of it, then what you hope to achieve is that you hope to see that all this flexibility is compromised in solid state or in aggregated form, and that would give rise to what is now called aggregation-induced enhancement of emission, or AIEE, which has become a catchphrase for 5-6 years. So we are not the first people to work on this. Thanks Group especially have played a very major role in establishing this field. And in this review published in 2015, they have sort of summarized pictorially in this figure what are the different pathways by which one can achieve AIE. So suppose you have an organic molecule that has active rotation. So here you have a carbon-carbon single bond. And as we all know, that you can have rotation about carbon-carbon single bonds without much fuss at room temperature. The other thing that is shown here is rotation with respect to a carbon-carbon double.
Sir, you are not audible.
Now,
Sir, this is Amrit. Everything is fine, sir. You can proceed.
okay. Can you hear me?
Yes, sir. Yes, sir. Yes, sir.
Can you see the slide?
Yes, sir. Perfect.
Yes, sir, you are audible. Yes, sir. Continue, continue.
Thank you. So if it's possible to unmute everybody else, it'll be good, because sometimes people are having some noise.
Sean, please check. Sean, please check.
Right, we'll proceed. Right, so now the thing is, here, what you see is rotation with respect to a carbon-carbon double bond. How is that supposed to happen? As we all know, as students of chemistry, it doesn't happen. If you have cis isomer, it's not so easy to go from it and get the trans isomer. Well, in ground state, yes. But suppose you do a pi star excitation. You have one electron in pi orbital, one electron in pi star orbital. So pi bond order is 0. Means the double bond has now become a single bond in the excited state of the molecule. So in that excited state, you can have cis to trans isomerization. This phenomenon is called photoisomerization. And photoisomerization is not something that is very unusual, or it's not something that we have to force to happen. It happens all around us. In fact, it's part of the vision process. And there are many other biological processes in which photoisomerization takes place. So suppose you have processes like that going on in some organic molecule, and then you form an aggregate. The moment you form an aggregate, in the rigid environment that the molecules now see, it's not so easy for them to undergo that active rotation. So you achieve what is called restriction of intramolecular rotation. So like the field of NMR spectroscopy, this field of materials chemistry is also replete with all sorts of fancy acronyms. So the acronym for restriction for intramolecular rotations is RIR. So when you have RIR, then you might hope to get strong emission in the aggregated form. Or suppose you have vibration. Once again, the moment you make a solid or an aggregate out of it, it's not so easy for the molecules to vibrate as freely as they were doing it in monomeric form in the solution. So once again, you can hope to get enhancement in emission, AIE, when you have RIR, and now it is called RIV. Right. So these are different ways in which one can achieve aggregation-induced enhancement of emission, AIE. There has been a lot of work worldwide in designing applications of these AIE molecules in their aggregated form. There have been applications in DNA visualization, protein fibrillation, bacteria imaging, photodynamic therapy, fingerprint visualization, and whatnot. This here is a paper that we'll refer to once again while talking about our own work. Here, this is an example of pi-stacked organic solids in which you can see this is a crystal that is glowing, a crystal that gives out light, of course, in solid form. It's a crystal after all. And there has been significant work in understanding the basics of AIE process, the phenomena. This is an example from our very own Professor T.P. Radhakrishnan's lab, in which they have studied the different aspects that are important in determining when AIE is possible, when it is not. Of late, AIE has found very important applications in biomedicine, cancer theranostics, biomacromolar sensing, in vitro cellular imaging, in vivo bioimaging, and this field is presently growing big time. So this is another very informative review by Tang, published a couple of years ago. So whoever is interested in this, I'd recommend that you go through this review. Now, before going into what we do in this particular field, since we have a large number of undergraduate students in the audience, let me, over the 5 minutes, present the very basics of steady state and time dissolved fluorescence spectroscopy, which are the main techniques that we use. So seniors, experts, and connoisseurs, please excuse me the next 5 or 10 minutes. This is only for the benefit of the students for whom this might be a little new. Now, I'm assuming that everybody knows what an absorption spectrum is, what an emission spectrum is. So when you have an emission spectrum, two parameters are of utmost importance. One is, where does it emit? When I say where, I mean at which energy. The choice of unit here is nanometer. The parameter of choice is usually wavelength. So the spectral maximum, more often than not, tells us about the immediate microenvironment experienced by the fluorophore. So where does it emit? At which energy? That is one important question to ask. The other important question, of course, is how strong is the emission? And to say how strong an emission is, the parameter that we use usually is fluorescence quantum yield or emission quantum yield, which is essentially a ratio between, well, how many photons are, well, essentially fluorescence quantum yield means how many photons are emitted per photon absorbed.
Hello, Dr. Mitra. I guess we lost Mr. Datta. There's a network connection on his side because of which he's out of the meeting at present.
Okay. Don't worry.
I'm back. Do you hear me?
Yes, sir. We can hear you. Yeah. Yes, sir.
Sorry about that. For some reason, my internet connection has been playing.
Okay, sir. No problem, sir. No problem.
So don't worry. If I go out, I'll come back as well.
Okay. Sir.
So what I was saying is that fluorescence quantum yield essentially is a number of photons emitted per photon absorbed, and in the simplest case scenario, it would be less than or equal to 1. Right. So this is a very simple experiment that one does. The other experiment, which has now become commonplace, is time-resolved fluorescence. Here, we try to monitor the fluorescence intensity, and well, we try to monitor the time evolution of fluorescence intensity. You can see fluorescence intensity is there on the y-axis. On x-axis, we have time. And when I say time, I do not mean seconds or hours or even microseconds or milliseconds. I mean femtoseconds and nanoseconds. So to do this experiment, we excite the molecule at a wavelength that it absorbs, but we excite using a pulse of light. I hope we all know what a pulse is. Pulse means light that goes on for a very short while and then remains off for a long time, and then it can come on again for a very short while. In our case, the light is on for, depending on which kind of experiments we do, the light is on for some 100 picosecond or so, or for some 100 femtosecond or so. Picosecond is 10 to the power minus 12 second, femtosecond is 10 to the power minus 15 second. So this is what we do. Now, what happens when you excite these molecules with a pulse of light? We're not working with one molecule here. We're working with a large number of molecules. Let's say Avogadro number of molecule, which is like billions of billions. Okay. Once again, for students to try and figure out how many crores of crores there are, or crores of crores of crores in Avogadro number, that exercise would convince us how big that number really is. Right. So we're actually working with that number of molecules here. We're working with moles. So what this pulse does is that it promotes a lot of those molecules, millions or billions of molecules, to their excited state. And then it goes off, right? This is what the pulse roughly looks like. What happens when the light goes off? So all these molecules which are in their excited state, would they come back to the ground state right away? Not really. They spend some time in the excited state, and different molecules spend different time. It's statistical. So since you're looking at a population of molecules, what happens is this population decays over time. And this time is typically from femtosecond Right. So we were here. So the situation is pretty much like what happens for radioactive nuclei. They're left to decay on their own. And I think all of us will remember that radioactive decay is a first order process. So the decay is exponential. So here also, the decay of the excited state population in the simplest case scenario is exponential. And we follow this by following fluorescence intensity. At any time after excitation by the pulse is proportional to the excited state population. So in the simplest case scenario, the fluorescence intensity decays in an exponential manner. Here, it's convention here to use not k, but 1 by k, that is tau. This is lifetime, the time spent on an average by a molecule in the excited state. Now, fluorescence lifetime and fluorescence quantum yield are directly proportional to each other. Phi f is equal to kr tau, where kr is the radiative rate constant, and tau is the lifetime. Phi f, as you know already, is fluorescence quantum yield. So, as a rule of thumb, we can say longer the lifetime is, more emissive is the sample. More emissive is the molecule. Now, I told you that in the simplest case scenario, the decay is single exponential. Thankfully, it is not single exponential all the time, because then life would be very, very boring. Actually, in most of the cases, it is not exponential, and you get a decay in which, by the way, did you notice that I drew a line for an exponential decay? That is because the y-axis here is logarithmic. So more often than not, this decay in the semi-log plot is not linear. It is curved. So that is because there can be different kinds of molecules. There can be different kinds of environments. So you can have a lot of different kinds of lifetimes at the same time from the same ensemble. All right. So the most popular model to fit this kind of data is this, a multi-exponential model. Most popular, but not necessarily always correct. But this is what we'll stick to for today. Right. Now, whoever has studied fluorescence spectroscopy would know that there's something called Kasha's rule, which says that fluorescence spectra are expected to be mirror images of absorption spectra. Once again, God is kind, and it's not always the case. Usually, they are not. That is because excited state processes happen in molecules. You can think that these are excited state reactions. I talked about photoisomerization a little while ago. That itself is an excited state process. So very often, after excitation, there is some excited state phenomenon that takes the molecule to a different excited state, which is at a lower energy than the locally excited state. So the emission that takes place is at a longer wavelength or lower energy. So the driving force for the excited state process is change in electron configuration. The ground state and excited state have different configurations, so the reactivities are different very often. And signature of the excited states is, well, first of all, you expect to get a redshifted fluorescence spectrum, as I said. If you look at time evolution, you expect to see a fast decay in the blue end, because that is where the locally excited state makes a greater contribution and it has an additional decay pathway. And you expect to see a rise in the red end, because that red end emission is mostly due to this newly formed state, which is not even there at the time of excitation. Right. The way we do it is by using instruments like this, time correlated single photon counting. This allows us to do the experiments in hundreds of picosecond to nanosecond time scale. Femtosecond optical gating, which allows us to go down to femtosecond time scale. And this is femtosecond transient absorption. For this, I'm grateful to an SARB committee chaired by Professor Satyamurthy, which gave us generous grants to procure this instrument. With this, we can look at molecules that are not fluorescent, because transient absorption means you look at how color changes as a function of time post-excitation by a pulse of light. Okay, I'm not going to really show any data from this part today, but whoever is interested in knowing about further detail about the instrumentation and techniques and so on and so forth, last semester I offered this course on NPTEL, which is an online learning platform. This course was on ultrafast laser spectroscopy. But the course is now practically over. But a good thing about NPTEL is that all those video lectures are now going to be available on YouTube. So whoever is interested can go through those lectures. There we have discussed excited state processes, and we have gone into our lab and we have sort of shown how these instruments work. Okay, but we'll not talk about that today. Right. So this is another kind of instruments that we have now set up as Institute Central Facility, fluorescence, lifetime imaging, and microscopy. So let us just say that here you can look at lifetime, but this time under a microscope. With this, we have looked at a plethora of excited state processes in molecules and materials. Today, I'm going to talk about very briefly about two kinds of systems we have studied, systems that give fluorescence in solid state. The first one is of shift basis, started by my student Tuhin, who is now a postdoc in the University of South Bohemia, and being carried on by a student, Shoru, who's now taking the problem forward. So we started working on this molecule called cellophane, very, very common molecule. A lot of people have worked on this, extremely easy to synthesize. And the reason why we worked on this molecule is, first of all, the synthesis is so easy that we can do it. We are not Besides, if you look at the structure, it is very easy to see that this kind of a molecule would be good. Put in a metal ion here, it would form a stable complex. The question we wanted to ask is that, does such complexation bring about fluorescence? And the origin of that question is this. As I showed you earlier, a molecule that has very flexible structure is not like to be strongly fluorescent in solution. Cellophane does have there can be notation about this CC single bond, about this CN single bond. There can be photoisomerization. There can be a lot of things. But if we perform complexation, then we can hope that all the flexibility perhaps the molecule would become strongly fluorescent. The other possibility, of course, is that you can have heavy atom effect since you're introducing a metal ion, and you can have the system process, and that can kill. So what we're curious to see is which of these two effects predominate, which of these two effects win. We did two kinds of experiments. First of all, we made metal complexes. Secondly, we made solids out of it. Now, when we made metal complexes, then to cut a long story short, what we observed is that only with two kinds of metal ions, zinc and aluminum, we get enhancement in fluorescence quantum yield. Please note that fluorescence quantum yield is shown in logarithmic scale here. This is the fluorescence quantum yield of cellophane. This is the zinc complex. There is the aluminum complex. There is a really humongous amount of enhancement in fluorescence compensation. And the difference between fluorescence quantum yield of zinc complex and aluminum complex is substantial. And this is brought out in the lifetimes as well. This is the decay of cellophane. As you see, fluorescence decays in a matter of 60 picoseconds. And remember, if it decays quickly, then it is not going to be strong. Zinc complex excited state lives for a little longer. Aluminum complex actually has 1 nanosecond. May I request everybody to mute yourselves? Please mute yourself. Thank you. Okay. So aluminum complex is much, much stronger fluorescent than the zinc complex. The question is why? And to know why, we went back to literature, and it appeared that
I guess we have lost Mr. Datta once again. Let's wait for a couple of minutes to.
Well, I'm back.
So that he could join back.
I'm back actually.
Okay. Welcome, sir.
Oh, sorry about this. This is happening too many times. Right. So what I was saying is, can you people hear me?
Yes, sir.
Yes,
Yes,
we
sir.
can. Yes, please go
Yes,
ahead.
sir.
So in a dimeric complex, when these ligands come very close to each other, there can be a lot of excited state processes that can take place between these two molecules. Okay, you can have excimer formation. You can have some other other kind of interaction. So that is something that can favor what is called ACQ, right? So to understand this, we tried to crystallize these. We could crystallize the aluminum complex, and we saw that it's monomeric. So that is why it's strongly fluorescent. We could not crystallize the zinc complex, unfortunately, but mass spectroscopy convinces us that the zinc complex is indeed dimeric. So right now, we hypothesize that dimeric zinc complexes that are pi-stacked, there some additional non-radiative channels open up, and that is why it is not as strongly fluorescent as the aluminum complex. And this is supported by our experiments in solid state comparison between cellophane and the aluminum complex. For cellophane, in solution, if you remember, there is the lifetime is in picosecond. In crystal, the lifetime turns out to be in nanosecond. And we were very happy. That's what we want to happen. So we get AIE happening in cellophane. The problem with working with cellophane is that it's very unstable, even in crystalline form. So we'd rather work with the complex. The problem is, when we look at aluminum complex, which has nanosecond lifetime in solution, the moment we make a crystal out of it, we get a picosecond lifetime. So there's an exact reversal in trend between free-base cellophane and its aluminum complex. And the answer to this enigma lies in molecular packing. Free-base cellophane, when you make a crystal out of it, this is again X-ray crystallography data, we see that the molecules pack like this, and adjacent molecules are sort of in T shape. There's no pi-pi stacking. However, if we work with the aluminum complex, complexation planarizes the molecule. And in the crystal, these planarized molecules pi-stack. So it appears that that is what gives rise to some additional excited state interaction and opens up some additional non-radiative decay that kills the fluorescence to some extent. Now, if you go back to the zinc complex, that is how zinc complex is anyway. So this, we think, is a circumstantial evidence to convince us that the zinc complex is not all that fluorescent because of pi stacking, which opens up new non-radiative channels. And what we have done further is that we have introduced small substituents in cellophane, ethoxy and methoxy groups, and that has been enough to destroy this nice planar structure in the crystals. Now you see the crystal structures are puckered, and now we have aluminum complexes that have nanosecond lifetime. So, so far the take-home message is pi-pi stacking is bad if you want to make emissive molecules, emissive solids out of this kind of complexes. So what we are trying to do next is that we want to make emissive zinc complexes. Problem with zinc complexes is that they're almost always dimeric. So we move from cellophane to another molecule. This is what we call P, because in literature there was a report that here, even though the complex is dimeric, it's like this. It's not pi-stacked. It's a bridged complex when you use acetate anion. And in fact, we also got this bridged complex, and we got nanosecond lifetime for the zinc complex now. So now we can say more strongly that we should avoid pi stacking if we want a longer lifetime. Two things to note here.
Anindya, may I interrupt?
Yes, please.
Your screen is not shared.
Really? Okay. Let me try to do that. Sorry about that. Okay. Now it is. I don't know how many slides we missed. But in case that happens, please do tell me. Sorry about that. Okay, so what we see is that two things before going away from the slide. First of all, okay, it's great that now we have a zinc complex which has 6 nanosecond lifetime, but still the lifetime is not as long as the aluminum complex, and that might as well be because zinc is heavier than aluminum, and perhaps some ISC is taking place here because of heavy atom effect. Point number 2 is we are saying very confidently that you have to avoid pi stacking if you want longer lifetime. However, for other kinds of molecules, there have been reports, as I had shown you earlier, for pi stacked organic solids that are strongly emissive. So this may not be a very general rule. Of course, it holds for the kind of molecules we are working with, but this may not be one ring that rules them all. Okay. Well, I don't know whether I should tell the next story. The thing is this, there was some literature report that the same Salampi molecule gives monomeric zinc complex with ClO4 minus. So we tried to make this complex, the structure was reported. And once again, we get a 6.3 nanosecond lifetime, so which is great. But then the problem is we never got this monomeric zinc complex crystal. So what we get is this, a different kind of dimeric complex. So our contention is still fine. What we're saying is pi stacking cannot be there. Even here, there is no pi stacking. But we have not been able to reproduce this result. And then when we tried to access the original CIF file, it turned out to be corrupted. So we have not got a monomeric zinc complex. That's what I want to say. But the fact remains that if it is not pi stacked, then we do get a nanosecond lifetime here. Okay, and then we introduced another zinc ion to see what happens. I'll skip this part. This is the conclusion of this part of the story. And to give a very executive summary, all I'm saying is that starting with this kind of Schiff bases that are flexible, one can make strongly fluorescent organic solids, but pi stacking seems to be a problem if you want to do such a thing. Now, let me quickly, how much more time do I have? I sort of lost track of time. Do I have 10 minutes?
5 minutes, sir.
5 minutes, okay, great.
Yes. Oh.
So I will quickly go through the story that I actually wanted to tell here today. Another molecule that we have been working with, once again, very flexible structure. And we got this molecule from our colleague, Professor Anil Kumar. Work was started by postdoc Anushwa, and it's been carried on by another postdoc, Shomodipta. So again, this is a molecule that looks like can give us AIT because it has a flexible structure. So to start with, we did a very mundane experiment. We dissolved it in a good solvent, that is acetone, which dissolves it nicely. And we added a bad solvent, that is water. And from absorption spectrum, you can see that absorption spectrum is getting broad and well messed up, which says that we are actually making aggregates. And this is what happens. In acetone solution, the acetone solution is actually non-fluorescent. But when we add water, we form a little turbid dispersion that is strongly fluorescent. And you can see that from the spectral shift as well. I've not shown the lifetime. And what is interesting is that we see that we get some nanorods that are formed from these solvent mixtures. So we have been able to make luminescent nanorods, and we can get fluorescence from solid state, presumably because all this segmental motion that is there is stopped. The problem is this. As you can see, these nanorods are not very regular. And then you do the experiment on different days in the same solvent mixture, you get nanorods that are not always the same. So this is not a very reproducible system. So we thought, can we bring in some order by adding surfactants? So we added something very, very simple, Tritonix 100, very common surfactant. And as you can see that there is an increase in fluorescence quantumile, there's an increase in lifetime. And here, one thing I should say here is that, once again, there are millions of papers on interaction of organic molecules with surfactants, but generally there you'd use small amount of organic molecule, large amount of surfactant. Here we are using stoichiometric amounts, right? 1:10, 1:60, something like that. So now what we see is we get good looking nanorods. And they are definitely fluorescent. You see these nanorods not only under electron microscope, but also under a confocal fluorescence microscope. Very nice looking nanorods. And this experiment is definitely reproducible. Of course, the problem with showing this FEXM kind of data is that people say that maybe that is not what you have in the dispersion. Maybe that's what you're getting when you take everything out of the solution phase. Very valid concerns. So we did cryo-TM experiments. There also we observed similar nanorods. Right. And then with this new toy that we have, fluorescence lifetime imaging and microscopy, we tried to monitor this. We tried to see how these are formed as you increase the amount of surfactant. What you see on the left-hand side is fluorescence microscope, fluorescence image of the of whatever we see. What you see here is the same fluorescence image, but not fluorescence intensity. This color that you see is not the actual color of fluorescence. This is pseudo color given according to lifetime. So if you look at this plot, this is amplitude versus lifetime. So amplitude is essentially contribution of the lifetime or contribution of the component to the particular lifetime. So we're essentially saying how much of what fraction of the species have what kind of lifetime. So when we start with just DBMPT, we see that the lifetime is about 1 nanosecond, and it's fairly, so this color is what is used for about 1 nanosecond. When we add surfactant, mute yourselves, please. Sorry. When you add surfactants, now you can see two kinds of colors here, right? That's because this is for small lifetime. This is for larger lifetime. You perhaps see it better in this plot, where you see two kinds of distributions. So here you have these what I call homoaggregates plus surfactant-induced aggregates. Two kinds of aggregates, and we see that surfactant-induced aggregates actually have longer lifetime and are more strongly emissive. So as we go further, we keep getting more and more of surfactant-induced aggregates. Not only that, the nature of the surfactant-induced aggregates changes, as is seen by the displacement of the maximum of this distribution from here about 2 nanosecond to here about 3.5 nanosecond. So now at very high concentration of surfactants, now here see the distribution is broad, the distribution becomes narrow. So most of the emissive species exhibit a similar kind of environment. That is what we get to learn from this experiment. Right. Sorry. So this, I meant this to come first, it has come last. So of course, this is the amplitude that we have talked about that is there in the y-axis. Next, finally, we are trying to go towards an application where we can make things that emit light. And we want to do it in solid state. And then what is the purpose? We want to make, let us say, an LED, which is made of this organic material. It has to emit white light. So what we did is we added perylene to this system, and there we observed FRET, Foster resonance energy transfer. And in this admixture, we can see strong white light comes out. Nearly perfect, strong white light. That is what we observe here. And we could add some gelating material and make this a solid white light emitting substance. Okay. Next, we want to do something else. Triblock copolymers. Triblock copolymers are polymers in which you have hydrophilic and hydrophobic parts. These are the hydrophilic moieties. These are the hydrophobic moieties. We worked with two kinds of triblock copolymers, P123 and F127. In both, the length of the hydrophobic core is the same, but length of the hydrophilic exterior is different. Okay. Using this, we wanted to see whether we can induce AIE. The good thing about triblock copolymers is that they set by themselves and they set very nicely. So you'd get solid anyway without much hassle. So to cut a long story short, once again, we get a strong enhancement of fluorescence, and something interesting happens. And that is what we see under the microscope using fluorescence intensity as well as fluorescence lifetime. We see that with FP123, we get spheres, nanospheres. With F127, we get nanorods. And if you look at the lengths are actually in micron scale, which is very different from the micelles formed by these triblock copolymers, when they are by themselves. So these large aggregates that are formed are not just because we have tri-block copolymers there. They are formed because of interaction of the tri-block copolymers and our organic molecule DBMPT. Now, why we have spheres here, why we have rods here is something that we have not understood yet. We are trying to collaborate with people who do simulations of systems like this. Hopefully, we'll have an answer in a few months. But once again, we can follow this formation of these aggregates very nicely when we looked at it under the microscope and we looked at it using lifetime. Once again, you see we have homo aggregates, and then with progressive addition of the surfactants, we get of the tri-block copolymers, we get this tri-block copolymer DBMPT conjugate, which has much longer lifetime. Okay, and here you can see that if you look at the rods, not all parts of the rods are same. Different parts of the rods actually have different lifetime, meaning that there are different microenvironments. So to conclude, what we see is that DBMPT is a good AIE molecule. We get a heterogeneous distribution of fluorescence aggregates if we use solvent mixtures, but we can bring in a lot of order in the system by using external agents like surfactants and block copolymers. I have not shown you the data of imaging of cells that we have done with this DBMPT and tri-block copolymer aggregate because it's a little premature to show that, but maybe next time we get to meet somewhere, we'll be able to show how we can use this in bioimaging as well. With that, I'd like to conclude with thanks to all students, postdocs, collaborators, especially those who have contributed to this work, Tuhin Khan, Sharmishta Das, Shoradip Dasgupta, Anusha Mishra, Shomadipta Rakshit, Anil Kumar, our collaborator. And before ending, let me just say something since so many students are here. Professor Satyamurthy had talked about quantum chemistry. It just happens that next semester, I'm teaching this NPTEL course on quantum chemistry and atoms and molecules. So already about 700 learners are enrolled. So if any UG student is interested in enrolling in this, you're more than welcome. With that, let me thank you and let us hope that we'll meet in happier times in person. And I hope that we'll see many of you in our beautiful campus, which boasts of not only state-of-the-art facilities and excellent students and a lot of good research going on, but also we have this amazing collection of flora and fauna, some of which you see here. Thank you very much.
Thank you, sir. Thank you, sir, for your wonderful presentation.
Thank you, sir.
It's always been such a pleasure to listen to you as always. Thank you, sir.
Thanks, sir.
Sir,
Dr. Mitra, you are on mute.
Thank you, Professor Aninda Datta, sir, for your enthralling presentation. It was such a pleasure to listen to you as always. Thank you, sir, for inspiring us and guiding us. I would now like to welcome Dr. Provod Chobe, the former Senior General Manager and Head, R&D Center, BASF, former Chief Mentor, Innovation Hub, Nehru Science Center, former Regional Director, YCMOU. May I now request, sir, to take over.
Okay, thank you very much. Good evening, everybody. It is my pleasure to be part of this prestigious seminar organized by Association of Chemistry Teachers. My main theme today is to present certain very interesting applications about chemistry. We all learn chemistry, we learn theoretical chemistry, we learn different kinds of chemistry, and ultimately the proof of the pudding is in eating. Unless the applications are successful, the chemistry is not recognized by the world. And these very interesting applications I am going to present to you. The purpose of this presentation is we as teachers at all the levels. We should, I think we should, whenever we teach students right from undergraduate to postgraduate to even doctoral students, I think if we make them familiar with these futuristic applications, they will be quite charged up with chemistry. And even the students who don't like chemistry, they will start liking chemistry, because once we tell about the applications, students realize why they are learning. And this is the entire purpose of my presentation today, that as teachers, what are all the things we should project to our students when we are teaching. And that's why I'm just showing you about 70% of these applications are not yet materialized. They are not seen the real world. However, they are in the pipeline. And about 30%, I would say, are already in the market. But it is very interesting where the chemistry is going to take us in future. So let me start with some of the very interesting. Before going for applications, what is the public perception about chemistry? When we talk about chemistry, a layman thinks Bhopal. That is the first thing comes to mind. So it's a negative perception. Accidents. Every now and then we read in the newspaper some accidents in the chemical factories. Then pollution from factories, plastic waste, dirty seashores. And very funny, the last perception what I have written, once I had been to one particular college in South India, and I was just talking to the students there. It was an engineering college. And I asked, it was a girls' college. I asked them, how come you have taken IT as your subject? And because one girl was telling she used to like chemistry, but she decided to take IT. I said, why? She said, there are many reasons, she told, but she, very honestly, let me tell you, sir, in my undergraduate laboratory, all other laboratories had stools to sit, but chemistry lab didn't have any stool to sit. Okay, jokes apart. But okay, these are the perceptions about chemistry. Chemistry lab is dirty, smelly, etc., etc. So how to remove this negative feeling about chemistry from students' mind? I think that is the responsibility of we teachers. So as chemistry teachers, we have the major responsibility to change this perception. Let us see what we can do. The current scenario is, as far as teaching is concerned, for many students, chemistry class is not fairy tales like class, it's a drag. In some colleges, faculty members don't find time, and so chemistry teaching is only to complete syllabus. This is unfortunate but true. Some teachers fail to create interest in chemistry. In some of the colleges, difficult theories are taught in dry manner without explaining the application. So especially the undergraduate students who are supposed to take chemistry, they get discouraged. No special efforts generate optimism while teaching chemistry. Whenever chemistry is there, there is a sort of pessimism among some people. Chemistry, smell, accident, etc., etc. But we don't tell chemistry as a solution provider. And that's why in my presentation, whatever innovation I'm going to show you, these are all solution providers for future. And as far as research is concerned, chemistry research needs to have the oh wow effect. And interesting innovations need to be boosted, and focus on novel application needs to be enhanced. And let us see what are the applications which are really we can project to our students. Let us see the unbelievable current innovations based on chemistry. MOF, we are all, as a chemistry teachers, we are aware of metal organic framework. But where all it is going to be applied, or wherever or the pipeline experiments have been successfully conducted, let us see. Number one, gas storage in a confined place. Like whenever we teach inorganic chemistry or organic chemistry, students know about the metals, they know about organic ligands, etc. But what is the use if metal and ligands are used together to form MOF? Where it is applied, the students have to know. Selective absorption and separation of specific gases, like we can absorb carbon dioxide, we can absorb different, we can use it as a fuel cell. Then for deodorization, chemists have found out the molecular size of various odorant molecules which cause some bad odor, and the MOFs can be made specifically which can absorb those odorized molecules, and deodorization can take place. We had done some work in our laboratory few years back about this deodorization, that in our sweat, when like in I live in Mumbai, every day it is so, now that the temperature is so high, the if you go out, it is sweating, and at the end of the day your shirt or blouse is full of sweat, and the bacteria react and they form some odoring molecule, which the sizes could be found out, and MOF can be designed to trap those molecules. In addition to that, there are technologies available to make capsules, very microscopic capsules, and you can put perfume, and you can apply these perfume capsules on your shirts and blouses. So the odoring molecules are absorbed, the bad odor molecules are absorbed, and perfume smell comes for your shirt or blouse. So this technology is being explored by chemists. Then there is a successful experiment on water from air. Even with 20% humidity, chemists have tried that 1 kilo of specific MOF can absorb 2.8 kilogram of water, and you can get 2.8 a liter of pure water. So this is used for water purification also. You can purify pure water from other impurities. So once these technologies are refined, chemistry is going to change the world. And this is the message we have to continuously give to our students. This is just an example of MOF. The general structure, I think we all as teachers, we are familiar with MOF, metal organic framework. And the second picture shows some futuristic, very small, tiny MOFs which can absorb gas, so can be used as gas cylinders for future. Now, when we are teaching latent heat of fusion, I remember my school days or even college days, I really didn't understand what is latent heat of fusion at that time. I know it has something to do with the solid melting, and also in the second picture I have shown the typical experiment we conduct in the undergraduate college, that you set up an apparatus with very accurate thermometer and then check the temperature. When the temperature remains stable, that is the melting point, and you draw a graph like I've shown in the third picture, and whenever the graph is a straight line, that means that is the temperature, which is the melting point of that solid. Yes, now at this age, I think I understand it, but I'm sure students at the undergraduate level or even at the school level, they don't really understand what is latent heat of fusion. They just memorize the definition. But how about if we really tell them about a very interesting and fantastic application where it is applied? Let me show you in the next picture. This is a chemistry car, and this car was kept in 2013. It was kept in 6 different cities in India. During German year in India, we had kept it for 15 days each. This is a totally polymer car, no metal except engine. Everything is polymer, and very special polymer, engineering polymer, which is very lightweight, and the car is very lightweight. Another interesting thing is, if you see at the bottom, all the parts are made up of very special polymer, very lightweight, including spark plug. And another interesting thing of the car is, the second picture shows the roof of the car is made up of solar cells. So during daytime, no fuel required, no diesel, petrol, and the car runs on solar energy. But the most interesting part, why I showed you about that latent heat of fusion, the last picture you see, it's a seat. It is known as a cool seat. Why cool seat? Because chemists have coated this seat and the dashboard and the steering wheel of the car with very microscopic polymer capsules. These capsules contain waxes of very low melting point, mixture of waxes. So if you keep a typical car in sun, what happens? The car gets hot, the seat gets hot, the steering wheel, dashboard gets extremely hot. It's impossible to touch sometimes. But in this specific car, where everything is connected, where everything is coated with these microcapsules containing waxes of low melting point. The seed remains cool. The seed remains cool because the sun's energy is absorbed in melting the wax and the temperature does not rise. And this is exactly what we know as latent heat of fusion. And if we can explain this example or say similar examples, I think students will understand the concept of latent heat of fusion. Let me tell you about now this hemostatic gel, which can stop bleeding in a second. You all know that from traditionally the barbers use potassium alum or anhydrous sodium sulfate. These are vasoconstrictors. There is a contraction on the blood vessels, and that's why bleeding stops. But as long as these vasoconstrictors are used, the barber's work is done if there is a bleeding during shaving or haircut. But what about slightly more amount of blood flowing? The synthetic granular mineral zeolites composed of oxides of silicon, sodium, and magnesium have been used by chemists very successfully. But in 2010, chemists tried a very different application based on a natural product on veterinary use. It was to stop blood in animals, and it was like blocking the blood. Like when a plumber stops water flowing from a pipe by putting some M seal or araldite or something, this particular product serves exactly the same purpose. So now chemists have developed very special polymers which can be used on the blood vessels by physically and mechanically stopping the blood flow in a second. And this is going to be the future of wound dressing, which will have a very drastic effect on first aid. Now, we all know about the fluorides in toothpaste. There is a dilemma whether to use fluorides or not to use fluorides. Some people say fluoride is harmful. Some people say fluorides will fill up the cavity. Yes, both are right. But chemists have, along with biologists, have tried to synthesize the bacteria to fight tooth decay. And trials are going on to add it to the toothpaste as additive so that without fluoride, we can have the excellent effect of stopping the tooth decay. So this is what chemists and biologists together have very successfully done at the laboratory stage and awaiting the final launch. Now, let us talk about contact lenses. Almost 30–40% people use contact lenses. Contact lens history is a very old history. In 1800s, the glass contact lenses were used for the first time. I mean, if you read those accounts, it is horrible. There used to be protruding metal support from the retina, and a glass was on top of this support. I can't believe it. I mean, even if one particle goes in our eyes, we are so uncomfortable. I don't know how those people used to tolerate this entire metal frame on the retina. But anyway, by 1930s,
Sir, you have muted your mic. Can you please unmute?
okay, is it audible now?
Yes.
In 1930s, rigid plastic contact lenses came, PMMA, that is polymethyl methacrylate, but there was no oxygen permeability for it. Then the design improved. Chemists could come out with silicones and fluoro compounds which gave better contact lenses. Then came the era of soft contact lenses where PHEMA, that is polyhydroxyethyl methacrylate hydrogel based lenses. These are highly water absorbent hydrophilic polymers, but they are water insoluble. Then came silicone hydrogels. These are even better oxygen permeable, but they are hydrophobic. So chemists designed, modified these hydrogels so that the polymer became hydrophilic. Then came the next stage of contact lenses, that is the contact lenses which can deliver drugs, the phenyl boronic acid based polymeric micelles for ocular drug delivery. So today the contact lenses which are in the pipeline will be soft, natural feeling, lubricating the eyes, oxygen supply will be there, antimicrobial effect will be there, antifungal effect will be there, and drug delivery will also be there. So this is going to be the future of contact lenses just because of chemistry. So chemistry can really change the world, the polymer chemistry. And this is what, when we teach polymer chemistry, we should tell all this history to our students. Then let's come to the next. We all are aware about the pollution caused by uncontrolled use of pesticides. You can see in the middle picture how much pollution is caused. The first picture, you can see the trace amount of pesticides which are sticking to the crop. And the third picture shows the acute effect of contact with the skin of the pesticides, some harmful pesticides. So how to solve this problem? Chemists are really working hard to solve this pesticide problem. On one hand, there will be at least 10 billion population by 2050. And if we want to make sure that this population gets feeding, we have to ensure that the crops grow, there are no pests. But at the same time, how to solve the bad effects of the pesticide? Chemists have come out with several solutions. I'll show you one picture. This is an electron microscope picture, 1 lakh times expanded. This is a fungicide with a built-in timer. So only when the fungicide is required by the plant, the timer breaks open the fungicide ball and fungicide comes out. And this is the way of future pesticide delivery. And this will reduce the pollution substantially. Another very interesting aspect is, you must have seen IUPAC on its 100th anniversary came out with a list of the top 10 innovations which are in the pipeline that will change the world dramatically. And on top of this list is nanopesticide. This nanopesticide is still at the trial stage. No bulk trials have been taken, but there have been successful laboratory scale trials, and this nanopesticide will not disturb the ecosystem. For example, the picture shows a honeybee. Nothing will happen to honeybee, but the pests which are harming the particular flower or particular plant will get killed. And this is going to be the future of pesticides which don't pollute the atmosphere. Now coming to the pollution because of chemical factories. See the amount of fumes and other air polluting reagents that is coming out from factories. In the middle picture, you will see the big machinery, heavy machinery that gives noise pollution. In the third picture, you will see water pollution caused by chemical manufacturers. And how to avoid this? That's a big challenge for chemists. And chemists are working hard. And this is one of the solutions which chemists and biologists together have come out. That is white biotechnology. A fungus as a living factory. Specific plant species or fungus or other living things are being developed which will deliver specific chemicals in bulk without causing any problems, no noise pollution, no water pollution, no air pollution. And this is going to be the future of chemistry and chemical manufacturing. Now about coming to the plastics. We all know plastic is bad. We always say plastic should be banned. Many municipalities have banned plastic. But is chemistry there to ban things, or is chemistry there to solve the problems? Whenever I go to colleges to give lectures, I ask the students, do you agree with me that plastics are good or bad? Most of the students say, no, plastics are bad. Then I tell them, okay, first thing what you do is you throw your laptop in the garbage, you throw your mobile, because they are all made up of plastic. Even this garbage bin is made up of plastic. So how do we solve the problem? Chemistry is to solve the problems. And yes, chemists are solving the problems. In the second picture, you can see this bottle. Within 6 weeks under the soil, the bottle has biodegraded. So this is biodegradable plastic. Chemists have come out with a solution for future plastic. Many successful trials have been implemented and the products are in use. For example, in tea estates, when the saplings are used, they are transferred from one place to another using this biodegradable plastic bags, and when the saplings are put under the soil, the bag automatically gets degraded. No need to cut the bag, no pollution, nothing. This is just one of the use. There are many other uses people are coming even for packing material. So chemistry is there to solve problems and to come out with solutions and to change the world. This is what we have to embrace our students. Now, chemistry in construction industry. We all know about the lightweight concrete bricks, which is already available in the market. This is because of the innovations in inorganic chemistry. Then we all talk about rainwater harvesting. Rainwater harvesting is possible only when the tiles are porous, and chemists have come out with porous tiles. In India also you'll see many porous tiles which percolate water underneath, and it is stored under the road and can be recycled. Then this third application which we see in the truck, this is a common picture today on the road. Concrete taken from one place to another, liquid concrete. This is possible. Like in my childhood, there were no such concrete carrying trucks. Concrete had to be mixed at the site itself in small hand mixers. But today it is possible to transport bulk concrete from one place to another because of polymer chemistry. There is a specific polymer known as superplasticizer in common man's language. This superplasticizer keeps the concrete particles separate and in the fluid condition as long as the drum is rotating, and that's why we can transport bulk concrete from one place to another. Again, chemistry of polymers. And another fantastic application which is in the pipeline is concrete, which is transparent like glass. You throw stones and concrete will not break. And this is again because of innovation in inorganic chemistry. So the world will be changed because of chemistry. Now coming to the electronics. Do you remember the big bulky TVs which used to take two people to lift the TV? Slowly we moved to LED TV, and now last few years we have moved to OLED TV, OLED, that is organic light emitting diode. Just a thin plastic sheet and organic dyes molecule coated on it, electricity is passed, and now the TVs have come in the international market, which can be even rolled and folded like a mattress, like a chatai, and you can just fold the TV, roll the TV and take it. Wallpapers have come. Yes.
इनके नवा कपड़ा वाला कल बरहुई देंगे तो ये कपड़ा पहन
Wallpapers have come which can be OLED based. So if you are in a different mood, change the color of the wall. In the morning, it can be a cool colored wall. In the afternoon, it can be a bright colored wall, etc. I heard even for Navaratri, saris have come, which every day you can have different colored sari by just by switching a switch. So this is all OLED. This is all organic light emitting diode, organic chemistry. And this application should be told. Even OLED newspaper is in the pipeline. Just a plastic sheet connected to internet and electricity, so you can watch the news on a plastic sheet. So this is what is the future of chemistry. Now coming to textiles field. In the textiles, we all know artificial skin is actually, it is not a leather, but it is like a textile. And to cure the burn wound, chemists have come out with a solution of artificial skin. I don't want to go into details. But on top right hand side, I have shown you a lotus effect shirt. A lotus leaf, has a peculiar property, lotus flower and leaf, that you have a drop of water and it takes the entire dust and leaf or flower remains totally clean. And people have designed shirts based on this technology. In India also, there are a couple of mills which sell these shirts for 2,000 to 3,000 rupees. You must be seeing TV advertisement every day for lotus effect trousers. So it is readily available in the market all over the world. And I remember I had taken part in the Science Express train. I had played a very leading role in the first round of Science Express all over the India in 2008. That time we visited 52 stations and 25 lakh people visited the Science Express train. I had kept this experiment. One of the experiments what I had kept in Science Express was this lotus effect. People used to come, they used to get one handkerchief like a piece of cloth. They used to treat it with lotus effect chemicals and then put dust, put tomato sauce, put dal, anything. And even me and my colleagues used to wear a lotus effect shirt. And we used to challenge people, yeah, throw dal on us, throw tomato sauce on us, nothing will happen. And people used to be so thrilled. Oh, wow, chemistry is so nice. I remember, and I think it was in Bihar on the Patna station or something, one small girl came to this Science Express train and she asked my colleague who was on the train, sir, can I bring my t-shirt tomorrow? Because now Holi, Rang Panchami is coming next week. I would like to play Holi with this lotus effect t-shirt. So nothing will happen to my t-shirt. Next day, the train was at some other station. She came with her parents, brought a t-shirt and got it coated. And believe me, next week she called us. She said she played Holi with that t-shirt. Such a fun. Nothing happened to her t-shirt. It remained white. Lotus effect. So people get thrilled when they do something with chemistry. The first picture on the left-hand corner top, it is not an actual picture of a hollow thread, but I just to give you idea, I have projected this as a hollow thread. This hollow thread contains organic alcohol, which is liquid, a specific alcohol. We all teach chemistry to our students that alcohol gets oxidized to aldehyde and acid, carboxylic acid. So this particular alcohol, when oxidized, it gives solid aldehyde and solid acid, solid carboxylic acid. So if a shirt or blouse is stitched with this thread, then if the blouse is torn for some reason, then the alcohol, which is liquid, will ooze out, will come in contact with the air and will get solidified because it has formed aldehyde and acid. So shirt or blouse will get automatically repaired. This is what is known as self-repairing shirt. People went further. They even added some metal wires so that internet message can be sent on mobile phone. If a marine or if a military person gets a bullet wound, the shirt will get torn and military headquarters will get a message that such and such person had a wound. So this is how far the chemistry is going, and these are the very interesting things about chemistry which our students should know. Now, one innovation I'm going to give you about chemical engineering. There is one process about synthesis of pheromone, and one of the steps of this pheromone synthesis is acid catalyzed conversion. So acid is added to the precursor of the pheromone and it gets converted into the final pheromone, and then the acid has to be neutralized. Now the trick comes here that acid cannot, this particular stage, it is very water sensitive and it is highly water soluble also. So you cannot really use aqueous base to neutralize it. So you have to somehow get a solid salt, and then the salt has to be filtered, washed with solvent. The pheromone has to be separated. It's a very tedious process, requiring big reactors of 2 tons or something, requiring about a week to filter it, wash it, recover, etc., etc., etc. So what innovative ideas chemists had? They decided, why do we want to use inorganic base to neutralize this acid? Why not use a particular organic bulky base which will react with the acid and will form something what we know as ionic liquid? And they did this, and now instead of getting a solid salt, separation, filtration, washing with solvent, it was just the separation of ionic liquid, which is a liquid, and pheromone, which is also liquid in a separate phase. It was just the phase separation in a separatory funnel. And why do you require big reactors now? You can do it as a continuous process. And can you believe how small. Earlier, the reactor was about 2-ton reactor for this pheromone process. And can you believe how small is the reactor today? It's a handheld reactor because it's just a tube. Add A, add B, stir it, and separate it. That's it. It's just a separation of two liquids. And this is a really innovative process because they use ionic liquid theory. So this is what the innovation of chemistry is. Now coming to another very interesting, I'm almost completing. I know the time is almost up, but last 1 or 2 slides. 3D bioprinting. Here chemistry plays a very important and central role in this very complex process. Ink is made up of living cells and biomaterials and growth factors. Artificial tissues and organs have been made. Original organ is initially scanned that requires specific chemicals for scanning. To avoid organ rejection, numerous chemicals are added. Chemicals are required for stabilizing of bioinks, and artificial tissues and organs can be used for drug testing and toxicological research or for education purpose, for dissecting. Near perfect heart, blood vessels, pancreas, bones, retina, etc. have been made very successfully by doctors, biologists, and chemists. In future, modified organs can be made. Why to have a heart with 4 compartments? Why not have a heart with some 6 compartments? I mean, future is unknown. We don't know what changes will take place. People can now modify the organs because of this 3D bioprinting, where chemistry plays very, very pivotal role. And this is what is going to be the future of chemistry. Now, another very interesting, repairing of spinal cord. In Rice University, of course, in South Korea, some experiments, pioneering experiments were done. Few other universities had also done, but very conclusive and interesting experiments were done by Rice University, and they used graphene nano ribbons, which are already used in aeroplane wings, containers for natural gas, etc. But here they used it for medical purpose. Rats were paralyzed by breaking their spinal cord into 2, and graphene nanoribbons dispersed in polyethylene glycol were applied. It stimulates neuron growth and it forms a conductive scaffolding. And the rats could survive, and almost 95% their spinal cord function was normal within 24 hours, and within 15 days, even the motor function was almost normal. So this is just a beginning. Nobody has used it for human beings, but it has a huge potential. I think this will be used for chemistry, will be used in all these things. Now this is my last slide. We have to support innovation, and innovation is respected everywhere in the world. I'll just tell you one story which I experienced and end my presentation. I used to go for a scientific conference in Europe every year for almost 25, 26 years. About 10 years back, when I went for this particular conference, the theme was automobiles research, and head of an R&D center, global R&D of a very famous automobile spare part. It's very famous spare part. And the person who heads the R&D was the chief guest. He gave a presentation showing how the future cars will be like in James Bond movie. They will be amphibian, they will go in water, they will go in air, etc., etc., etc. At the end of his presentation, he was projecting what will be the future automobiles, and then he showed Ratan Tata's photograph, and he showed that this particular person, I don't remember what was the name, some Ratan Tata or something, he said, because but he is thinking of coming out with a 2,000 euro car. And those days, 2,000 euro was roughly 1 lakh rupees. And all the scientists, more than 1,000 scientists sitting there, could not believe that how can an Indian come out with the innovation which no one has ever thought, a cheap car, lightweight car. The same conference I went about 6-7 years back, and that time Tata Nano was already on the road. And everybody was asking me, are you from India? I said, yes, I'm from India. Do you know Mr. Ratan Tata? I said, yes. Can you introduce us to him? What a great innovator. We never thought that such a small and such a lightweight car can be born. So people respect innovation, and that is what we Indians, we should always strive for innovation, and we as chemistry teachers should make sure that our students are always motivated for innovation. From these topics they'll at least get some motivation that they have to do some innovation with chemistry. Chemistry is not only to get grades and marks and to get degree, but it is there to change the world. And if they get this message, I think chemistry will be respected everywhere like anything. Thank you very much for your time.
Thank you, sir. Thank you, sir, for enriching us in such a way. Thank you, sir, for your wonderful presentation. Thank you very much, sir.
Thank you.
May I now request Professor Brijesh Pare, sir, the President of ACT, to deliver the presidential address. Pare, sir.
Yeah. Good evening. I am audible?
Yes, sir. Yes, sir.
I'm audible, huh? Okay.
Yes, sir. Yes, sir.
So a wonderful evening, and it was really scintillating chemistry we are enjoying this webinar. Shining chemistry, and really when we have a galaxy of scientists at one place in one time, why it would not be a scintillating chemistry? And it's a great pleasure and a privilege to, of course, to welcome our guest. We really have a pleasure having Professor Satyamurthy, the former director of Pfizer, then Uday Maitra from IC Bangalore, Professor Anindya Datta, Dr. Prabodh Chobe, and TV Prabhu, and all. Really, we enjoyed, and since 5 o'clock, the first speaker, Professor Satyamurthy is a stalwart in the scientific world. He has given a very, very interesting talk. Bonds are dynamic, not static. And there was a natural flow in his talk always, I've seen, and right from the Levy's concept to the latest point of view on the covalent bonding. And this is his greatness, the people, those who have done so much of real science, in the whole of the life, and now they want to share their experience and knowledge with the undergraduate students and the postgraduate student. So that's wonderful. And this year, SCT is celebrating 20th year of existence, almost 20 years. And when we met in February for our AC in the Homi Bhabha Center, Mumbai, and we decided to go in a big way to celebrate the 20th year of SCT establishment. And so we thought of so many things, but none of us ever had an iota of doubt that probably we will not be having a chance to interact physically. And but I'm really happy that because of this webinar, we are able to get luminaries of this kind, at one place in one time. And then we heard Professor Uday Maitra, who has always been an eloquent speaker. And I have seen Uday Maitra, he, apart from his, the high-end research, he loves to interact with young students always. And that is really very inspiring. Professor Uday, please keep doing this, sir. And thank you for showing us the Mona Lisa of organic chemistry. The multi-component reactions information was very interesting, and the examples you have taken was really, really great, and we all really enjoyed it. I hope the students will definitely get inspired. Professor Anindya Datta talk was really mesmerizing. He has demonstrated excellent applications of the solid state organic translators, and he has shown so many things, and what a research in fact it is. I hope the students will definitely enjoy doing it. And Dr. Prabodh Chobe has always been, he's a real scientist. He's a man from industry, but having a very deep rooted, a choice and a desire, and to be a teacher, and always a very popular speaker, and giving so many good things, And I have just worked a lot of time with him, and again he was very impressive. And so everything was wonderful, and really this is we are from chemistry, and chemistry is the central science, and both ways, right, from the biology and physics side, we are there is a intersection. And I think today, all the galaxy and the dignitaries of the science world have spoken. So I think I should just congratulate my colleagues in SCT first and foremost, Professor Prabhu, who is our General Secretary. He is again a stalwart. I mean, he leads us from the front always, and very encouraging. So I congratulate Professor Prabhu and Dr. S.P. Singh, who is the convener, who is the man who designed the whole thing. He conceived the idea of doing it, and he's a secretary of our East Zone SET, and Dr. P.M. Mishra from East Zone, Dr. Amrit Mitra, who is the executive member from SET, Dr. N.K. Bhattacharya, Dr. Arya, for organizing this wonderful webinar. And thank you very much. Thank you. So nice of you.
Thank you, sir. Thank you, sir. Thank you, sir, for your talk. May I now request Professor P.M. Mishra, sir, to give the vote of thanks for this particular program. May I now request Professor P.M. Mishra, sir, to take over.
I'm audible?
Yes,
sir.
yes, audible.
Yes, sir. Yes.
Okay, thank you.
Sir, you are not visible. So can you please switch on your video?
No, sorry.
Your video is off, sir.
Yeah, now it's okay. Thank you. Oh. It becomes off.
दूसरी समान जैसे हिटलर ने यूरोप का खात्मा किया वैसे ही चीन ने हानु करा.
It's okay?
No, sir.
No.
Why it
We
happened?
can't see you, sir. Sir, please click on start video option.
Yeah, I'm starting.
Left hand side, two options are there, Mr.
Yes,
sir.
sir. Yes, sir. Yes, sir. It is coming, sir.
Good. Yeah.
It is coming, sir. Thank you, sir.
It's okay now?
Yeah.
Yes, sir.
Very warm good evening to all. I am very much delighted to be a part of this scintillating webinar on the topic of scintillating chemistry organized by ACT Mumbai on the initiation of ACT East Zone. Dear friends, as we are all involved in this webinar can feel, and it is obvious from the responses received on the chat box that this webinar has really proved its importance of its own. Dear friends, this whole credit goes to our galaxy of legendary resource persons who are really the stars of Indian panorama of chemical education and research. First of all, I would like to thank Professor N. Satyamurthy sir, who is former director of Aisher Mohali and former president of our esteemed association ACT Mumbai, and Bhatnagar Awadi, for his very informative, wonderful lecture on the very common topic of chemical bonding. We are very much delighted to hear his lecture, and everyone is praising his lecture. I am also thankful to Professor Uday Maitra, Professor of Indian Institute of Science, Bangalore, for his very exciting lecture on the topic molecules that defy rules. Very interesting lecture. We are very much delighted. I am thankful to Professor Anand Datta, very excellent lecture on the topic quest for solid state organic emitters. And I'm very much thankful to Dr. Prabodh Chaubey, former Senior General Manager and Head of R&D Center of BASF India, for his very, very interesting and informative lecture on the topic fairy tale like future innovations based on chemistry. Sir, we assure you that certain chemistry will change the world, and we Indian chemistry teachers and our association is going in the same direction to change the scenario of chemistry education in India. My heartfelt thanks are to the participants, the most important pillar of any seminar, for their overwhelming response. Dear friends, I assure you on behalf of ACT that ACT will organize such seminars on concurrent relevant topics in the near future in different parts of India, and we seek your active cooperation in all the upcoming events like this one. Dear sir, I wish to thank the organizing committee for organizing such a wonderful seminar.
Sir, you have muted your mic. Please unmute.
And inviting the legendary persons as resource person. All the participants are very, very happy. They have learned a lot from this webinar, and they are saying that they will definitely change their idea of chemistry, and they will also teach the students in a more different way, in more innovative way. I am thankful to Dr. Professor Brajesh Pare sir, Professor and Head Department of Chemistry, Madhav Science PG College, President of this esteemed institution association ACT, and our good friends for presiding this session and also guiding us at every step for the successful completion of this webinar. My sincere thanks are to Dr. T.V. Prabhu sir, Adjunct Professor for Wilson College, Mumbai, Founder Secretary of ACT, who is tirelessly working for the advancement of ACT, and he is taking keen interest in each and every step whenever any program is organized in any part of the country. He is very much interested in that, and he helped a lot. This is why we are conducting such a seminar in different parts of the country, in different zones. My thanks are to Dr. Subhas Prasad Singh, Associate Professor of Chemistry and College Patna. He is Secretary of East Zone ACT and also National Coordinator of Contact. Actually, this webinar is brainchild of Dr. S.P. Singh, and he is the key person for organizing this seminar, this webinar in a very grand way. My thanks are to Dr. Amit Krishna Dey for constant support from the first day to till date, and you have seen he has nicely conducted the seminar. Very, very, very much thanks to Krishna Dey sir. Last but not least, my sincere thanks are all those persons, the person who provided the platform and all other persons who are directly or indirectly, who have helped us in organizing this seminar in this grand way. Very much thankful. We are very much thankful to all of you and hope your cooperation in our future endeavor also. Thank you very much. Thanks all. And I hope you will stay safe, long live. Thank you very much. Good night.
Thanks to ACT for organizing such a wonderful webinar.
Thank you. Thank you all. Thank you, sir. Thank you, sir. Thank you all. Please stay safe and good night.